Today, now I invite Professor Gil Markovitz, and she will speak about phase one analysis for quantum dynamical system on time scales.
And of course she might say that, but she's the postdoc advisor of my PhD student.
Jacqueline isn't here, so I can't thank her, but thank you, Serena. Tom's not here, but thank you. Well, Tom has already heard this talk, so that's okay. I gave this talk in Medlibo, more or less, and so I apologize to those of you who heard it last summer. But it's the only work I've ever really done on time scales, and I did want to talk about time scales today. And it's joint work with Sabrina. And I should recognize our granting institution. Okay, so happy birthday, Martin. And this is the paper, the one paper we worked on together. And it actually motivated this idea of how to use phase plane analysis for discrete systems. Okay, so that's Serena, everyone knows her. And this is Victoria Ralph. She was an undergrad student, and she prepared the GUI. There's a MATLAB standalone GUI for the difference equations. Can everybody hear me? Yeah, I don't need I think I'm good. Nobody needs it. They don't want to get any louder than I am. Yeah, so she was an undergrad student. She made a standalone GUI that creates these phase planes that I'm going to be talking about. And she wanted to become a medical doctor and very brilliant. We all, like everyone who wrote letters for her said, if they don't take her, I don't know who they take. But in any ways, she worked with me and she got so into math that she's now doing a master's in mathematics. She said she'd rather do that than be a doctor. So that's really exciting to get through with people. Okay, so the outline of the talk, we're going to look at why phase plane analysis hasn't been really used for discrete maps. We're going to overcome the problem for some maps. I'll demo this GUI that Victoria did, the standalone MATLAB GUI. It's in 3 flavors, in Windows, Linux, and Mac, that you can download for free. So I want to advertise that because I think it's a great tool for teaching undergrads. You could even teach high school students how to do this phase plane analysis. And then we'll look at two-species competition on unbounded timescales. So first I'll do it for ODEs, then for discrete, and then on timescales. So you can see, and we'll look at this model with preliminaries that Bashak has already done, so I can go through very fast. We'll choose the model and look at how we can use this phase plane for arbitrary unbounded timescales. Okay, so why standard phase plane hasn't been successful as it is for ODEs? Well, everyone here knows about how to use phase planes for ODEs. So we're using the theme, I'm using this particular model because we're going to use it for ODEs, difference equations, and timescales. And it's basically the phase planes are going to look the same in all the cases, and the dynamics are going to look the same, but we can justify it. So everybody knows, or knows it's like MacArthur competition model. We can find the equilibrium points, we can find the null points, and we can do a phase plane analysis. And if the parameters are such that they cross this way, so that the boundary equilibrium on the outside, it turns out that the interior equilibrium is totally asymptotically stable. We can prove that using the Poincare-Bendixson. But there's no Poincare-Bendixson theorem in discrete planar systems. Okay, so we can look at a recursive map that looks like this. And Sabrina and I have a paper, I guess I didn't give a reference, but we can show that this is basically a similar model to the competition model. You can derive this under the same assumptions. Logistic growth basically of the prey and the interspecific competition. And if you set this up, you get, you can find the equilibrium points by setting each of the alpines look exactly the same. They have the same equations as the Arthur continuous law. Okay. Now, I'm going to skip over to the Ricker competition. We're going to do an analysis of that model, but the Ricker competition model, this is a discrete model that you will probably be familiar with. Hello? Is it better? Okay. Okay, so this is the Ricker. This isn't the same model, but it actually has the same phase plane. Like if you look at the isoclines and the equilibrium points, the nullines, you get the same picture. And so the dashed curves are the nullines. These red curves are something I'm going to explain called root curves that help us do the analysis. But what I want you to see is if you start over here, you can jump into this region that's positively invariant when it's an ODE, but when it's a difference equation, you can jump right out. And then you can jump right over them both. So that's not very helpful. If you can't say that there's a positively invariant region and everything converges to the equilibrium. I mean, this is not very useful. However, these curves are going to give us information that will allow us to do a complete global analysis for the other model, and for many other models. We're just going to demonstrate it on the particular model that it works for, but it works in other cases, applications. Okay, so we see why people haven't been using phase plane analysis so much for discrete planar systems. So how do we get around that? Well, we introduced something called root curves. They're really just the pre-image of the nullines. Okay, so if we have, so everything, the blue is always going to be the x equation, the red is going to be the y equation, and we construct this operator LH and LK the following way. So if we find a nullline, say the y equals h of x is a nullline for the x equation, then we can write this operator, the g of xy, it's just a function, g of xy minus h of f of xy. And if we look at what that is, at x t, y t, that's x of t plus 1 minus h of x of t plus 1. That's going to tell us if it's positive, the next iterate lies above the blue nullline. If it's negative, it lies below the nullline. And if it's 0, it lies on the nullline. And so that helps us to understand if we're jumping where we're jumping. And similarly, we can do that for the y nullline as well. And if sometimes we have another system where it might be better to write it as a function, x as a function of y, we can do that as well. And then the operator would tell us if we're moving to the left, if we're jumping to the left or to the right of the nullline. Okay. And so we have this operator, and where it equals 0, we call that the root sets. And if we're on one side, it's going to be positive. If we're on the other side, it's going to be negative. Just like nullines go from positive to negative across the nullline. For the direction field, the root curves go from positive to negative, telling you if we're jumping above or below or onto the nullline. Okay, so the interesting thing then is to find the sign of this operator in the different regions in space. Okay, so the next iterate operator can only change sign across the root curves. And if it's expressed as an injective function, it only intersects its own nullline it only intersects its own nullline at an equilibrium point. And if the root curves associated with nullines with different equations intersect at a point, that point is either an equilibrium or the next iterate will land on an equilibrium. Because for discrete systems, you can jump right onto equilibrium points. It's not like ODEs where it takes an amount of time to get to me. Okay. So they have nice properties. And so if we want to do a complete global analysis of this difference equation, that's the analog of the Rosenzweig-MacArthur ODEs, we can do that by introducing these root curves and their signs, the sign operators. And so we can find the null lines, and we can find the operators and the different signs, and then if we do them as functions, y is a function of x, y is a function of x, then if the operator is positive, we jump above the curve, above the null line. If it's negative, we go below the null line. And if it's 0, we go on to the null line. Okay, so for example, if we have this set up for our equilibrium, our null lines, because the null lines can do different things, right? They can intersect different ways, so we can have different possibilities. We can have globally stable boundary equilibria. We can have an equilibrium in the interior that is a saddle, and so we have two globally stable equilibria, equilibria on the boundary that are initial condition dependent, and we can have a globally stable interior equilibrium. We could also have a whole line of equilibria, one generic case. Okay, so in this particular case, we have our null lines, and I don't even need the root curves, I just need the signs. I need the direction fields. So this says if I'm in this region, orbits are moving this way, this region this way, and in this region up to the right, and I just need the sign of the operator in some of the regions. So if I'm, okay, so here are the root curves, but I don't really even need them. And let's start here. So if I started here, for example, it says minus, minus, so I'm moving up, but I must remain below both null lines. And then I keep moving. Again, I remain below both null lines. I move in between the root curve and the null line, and then that says I have to. So now this is a plus minus, so I have to go above the blue, but remain below the red. Then once I move into this region, then I am trapped. It's positively invariant, and I'm moving up, so I have to converge to the equilibrium on the boundary. So I move in, and I move over. Okay, and we can see from different places. So here, I'm on the root curve, I go straight to the null line, and then to the, and you can see plus plus, I move down until I cross the red root curve, and then I move into that region. So I have a complete global analysis in this case. Okay, here they cross differently. The boundary equilibrium are on the outside, and I know that they are each locally asymptotically stable, but I don't have to know that. I can determine that from the phase plane analysis. I have my root curves, I have the signs of the operators, and then I know that in this region, I have to either go up to the equilibrium point, or I'm going to enter this region and get into this positively invariant region and converge there, or enter this region and get into this and converge there, and similarly from there. So I have a global analysis from the phase plane. I know that the E star is a saddle, and that EK, well, that one and that one are locally asymptotically stable, and all solutions that don't converge to E star, on the measure zero, the stable manifold that measure zero, everything else converges to one of those other boundary equilibrium points. Okay, and then here, so why am I showing you this? So we understood that because we have the root curves. But when we want to do this for time scales, the root curves could be time dependent. And so it will be helpful to not have to include the root curves and just have to know about the operators, the sign of the operators. And so in this particular case, I have the two null lines, and I have the direction fields, I can prove, or we can prove, Sabrina and I, that if we are in this region B0, we cannot get into B1. The only place in B1, this region that we could get to, is to go straight to this equilibrium point. Otherwise, we're going to get into this region or this region. And then we don't even need to know the sign of the root operators at both of the null planes. We only need to know a little bit. So for example, we only need to know that below this red in this region, they're both not negative, above they're both positive. So I don't need to know that this is positive or negative. And here I need to just know that these are both negative and these are both positive. And so since I can't get into there, I'm going to either go here, I'm going to get here, move up, get into here, converge there, or converge here. I don't even need the root curves. Okay, I just need the sign of the operators. Okay, here is the case of the global stability, and we can do it as well. The same arguments work, so I don't have to go into the detail. But this time, these equilibria are on the inside. They're actually unstable. This one is the global attractor for solutions that start in the interior of the first quadrant. And everything, we can prove everything converges to east. Okay, so again, we don't even need the root curves. We just need it. Again, we can prove that from this region here, you can only either converge to this thing or you never go into B except for this root here, and otherwise we know what's happening from just partial information. We don't need all of the signs of the root operators. Okay. Okay, so we created, and Victoria, the undergrad student, did all the hard work. This GUI that's freely available, you probably have to download something called Runtime from the MATLAB site, but it's free also. And you can download the GUI. And if you don't really want to download .exe files, because some people are nervous about that, you can download the script files if you have MATLAB and do it yourself. But this is standalone, so you don't have to own MATLAB or you don't have to have MATLAB on your computer. And so the latest version is version 3.1, and it is 3 flavors. Though I think we set this up about 2 years ago, and so MATLAB has upgraded. And so if there's bugs and you try it and it's not working, send me an email and we'll fix it, because we do want people to use it. Okay, so the syntax is, for MATLAB, you have xt plus 1 is equal to something like this. Then you need a dot times, and an exp, but otherwise a dot carries a square. But otherwise it's pretty straightforward. And this is what the GUI looks like. I would have demonstrated it, but it said it didn't have the runtime on this computer. So, and I didn't bring my own. But like if you start it up, this would be probably blank, and you have to hit, draw the thing. And then you have control of the axes, and you also have control of how many of these things are. Like you don't need it to be so busy, but you need it to be busy enough so you know what's going on in each region. And why do we have these funny things instead of pluses and minuses? Because sometimes if you have an application, the null plane, it could be a circle, right? And so you want to write it as a function, so you might have to write it as a function of x or a function of y. And if it's a function of y, I said it's up and down, so that's why these point down and up. But it could be that it's a function of x, and so that's why these point to the left and to the right, because it tells you if you're jumping over to the left or over to the right. Okay, so it's all automatic, and you can adjust with this how many of these, like get it less busy. But if for some reason your application you don't have enough, you can add more so that you know what's going on. But really, you only need to know in each region one direction, right? Because it's not going to change in this whole direction. The dark red ones are going to be up, the light red ones are going to be down, the dark blue are to the left, and the light blues are up. You might not be able to see the colors so well. I've been noticing in this room, it's hard to distinguish even red and blue. Am I right? Can you see the different colors? Yeah? Okay. Because there are actually two colors of blue, because there's a blue null line, so that's pointing to the right, and there's this blue null line, and that's pointing up and down. Okay, so and you can put in whatever, and then you can, yeah, so you can change that, and you might have to change, so this is telling you, you might have to change these, because you might want to, like, this has to go further down to know if you're above it or below it, right? So that's why you have some control of these. And then if you want to add orbits, you can add orbits. You can put your initial condition, and then you can say how many iterations you want, and then it'll add orbits. So if you're not even sure, like you could say start here and just have it put in a few orbits just to check that you understand what's going on. So there's lots of functionality, and if anyone is interested, I'm happy to demonstrate it privately. Okay, so here's that example of the Ricker that was jumping all over the place, and now we know why, because we have the red null line and the blue null line, and this is the blue root curve, and this is the red root curve, and so it's actually telling us that if I start here, I am going to jump into this region, and if I start here, I have to jump out of that region, look down here, and if I start in here, the things are telling me I have to jump across both of them. So it gives me that information as well. And so we've used it as well to say it was a predator-prey model. It can have at most period 4 things. So sometimes, like even in ODE models with Poincare and Dixon, you can't do complete global analysis with some models on phase planes, but you can do, some things. Well, it's the same. We can't do better than for ODEs, but it can tell us lots of things. Okay. So what about timescales? So on unbounded timescales, so the books that we refer to are by Bohner and Peterson, the Bibles, and we had a preliminary review this morning about timescales, so I can go through this very quickly, but this is all we need to know. So we're going to have a timescale, any non-empty unbounded set. In our case, we want it to be an unbounded closed set. We'll need the jump operator. You need to know when it's right scattered and right dense. So there is an example with left dense maybe. Braininess, the circle plus operator and the circle minus operator, and the RD continuous. Okay, that's all we're going to need for today. So first, let's think about the single species logistic model, because we want to write a model that's going to be a competition model. We'll start with the logistic model. We're going to use minus circle minus R, x sigma 1 minus x over k. X sigma is x plus the braininess times x delta. It can be solved explicitly and, in fact, much more generally in the book by Bohner and Peterson on page 18. They have a very general logistic equation. This is only one example of, it's a special case of their much more general example, and they have the general solution by setting z equal to 1 over x and using the variation of constants formula that Sabrina told us about on Monday. Okay, so why do we use minus circle minus and not just R or circle plus R? Well, if we used circle plus R, that's just R, and x sigma becomes this thing here, and then we would have to restrict our time scale to ensure that all solutions remain non-negative. However, if we use minus circle minus R, then we get this, and it's always non-negative. So that's what we're going to use for our logistic equation when we generalize it to competition. Okay. So we have our minus circle minus x sigma, and then all we do is we include the interspecific competition, and we can prove that analytically non-negative initial conditions and positive parameters will give us good solutions. So all solutions will remain non-negative and bounded. And what's nice about this, if our timescale is R, then it's just the ODE that I started out, the Rosenzweig-MacArthur. If instead the T is the integers, well, it's just the other equation that I analyzed for you, the other competition model that I analyzed for you. Okay, but it's more general. It's on arbitrary and bounded timescales. Okay, and so we can figure out what x delta is and add right dense points. This is just the usual derivative. And we can find the null lines. Again, we get basically the same null lines. So that's not an issue. We can find the equilibrium points, and basically there's the same equilibrium points. And like I said, solutions, we can prove that solutions remain non-negative and are bounded. So that's not hard to do analytically, but in fact we can, I'll mention that after. Okay, so then we have to generalize this idea of root sets, which we can do. So it's a formula. I'm not expecting you to memorize it, but we can find the root sets. But remember, I told you that it's not the root sets that are important because they are going to be time dependent sometimes. It's the sign of the operator. So, but again, when they're isolated points, the root sets are the pre-image of the null lines. And let's see what else I can say about this. And at a time point sigma, the y value is on the associated null line. If t is r and t is z, the root set is time independent. We've seen that, right, in general. But what's sort of interesting is that the root set can be time dependent, right? And so maybe that's a problem. And so we're going to look at quantum. That definitely is, the root sets are time dependent. And here's an example of what the root sets look like. And the higher you do the root set at a particular time, the further away it is from the null line on this side and on this side. So then you go, oh, well, maybe you can't generalize this to timescales because there's all these crazy root sets. But again, like I said, it's the operator that's important and the sign of the operator. And if you can know it in the important regions, then maybe you can do something. And it turns out that we can. So, so for right scattered points, the sign of the root operator tells us the same on which side of the associated null line the next iterate lies. So it's a sign of the operator that's important. For right dense points, it's like the ODE, right? And to obtain the global dynamics, like I said, we do not need to find the root sets, only the sign of the root operators in certain regions like we did before, and in some of the regions we only need to find one of the signs, just like we did before in the discrete case. Okay, so again, we can find the null lines, it's just a basic arithmetic, and from this we can actually, just from this analysis, if we hadn't proved that the first quadrant is positively invariant and the axes are positively invariant, we would get it from the signs of the operators. So we could get it from this analysis. And yes, the root curve, the operator looks complicated. It has possibly ugly looking coefficients, but we have control of the sign of those things, and it's not hard to prove the sign in the regions that we need to know the sign. And the same for the operator for the other null line. And we can also prove for unbounded timescales that if we have a two-species model, if there is a t in our timescale such that both components are component-wise monotone for t in the values of the timescale, then the solution converges to an equilibrium point. So if we know the direction field and we know whether we're jumping and we get into a positively invariant region, we're good. We can prove the global stability. And so here's an example where we have our null lines for an arbitrary time scale, and we can prove what the sign of the operators are, and we can then prove that we converge to the boundary equilibrium for all initial conditions. And so this is just saying that. So we would know, depending on which one is above and which one is below, which one we converge to, the boundary equilibrium at the top left or the one on the bottom right. Here, though, we can see that the root curves are, for the quantum, we have these root curves, but we don't need to know. We only needed to know the sign of the operator. Okay. And here's what I said about the B0 and the B1. It's the same as in the previous case. If we're in that lower quadrant, we cannot just go anywhere. We either go to the equilibrium or to one of those regions. So we have basically the same picture. We can prove it, and we get, in this case, the outside boundary equilibria are each locally asymptotically stable. Everything converges to one of them, except for if you're on the stable manifold of the interior saddle. Do that. We're doing not too badly. Yes, the root curves are really ugly, but it's not a problem. Okay? And similarly, this is the case when the boundary equilibria are on the inside. That's when they are both unstable, and the interior equilibrium is globally asymptotically stable with respect to solutions starting in the interior of the first quadrant. And again, we can do a complete global analysis because we only need to know these signs, and that's all we need. Okay, so got that. Oh, I'm doing great. Okay, my timing isn't too bad. So this is good. Okay, so there are some differences because the root curves are time dependent, and it depends on the scale, the time scale that you have. So for example, if you're at this point at different times in your time scale, so this is a case when you either convert, for different initial conditions you converge here, for other ones you might converge here, maybe on the, for measure 0 you converge there. But you could start here at different times in your time scale, so you could be at the same place but at different times, and you might go here for one set of times, and you might go here for the other set of times. So that is one difference. Compared to, say, the difference equations or the differential equations. Okay, and as I said, we prove that if we have our model and we have this component-wise monotonicity, we're going to converge to an equilibrium point. However, for some applications, if we have a right or left dense point, for numerics, we might have to think about what to do. It's sort of interesting. So let me just show you an example. Maybe you'll have some think about. Tell me what you think. I know Tom had an idea. Okay, so we're in this situation for this time scale. So 1 here, somewhere, 1 here, is both right dense and left dense. Okay. And if we start here, then we're supposed to go up here and converge to there. And theoretically, that's what we do. Okay, that's in theory what we do. However, I could run this on a computer for 1,000 steps, starting from that point 1, and only get here. Now, it's kind of weird because if it's an ODE, right, and I start there's like the points are even closer, right? And it takes forever to get to the equilibrium point. But here, like, will I ever get into that region to converge? Like, theoretically, we proved that, I think we proved that we converge to the equilibrium point. But numerically, we have to think about how to deal with it on a computer. So for some applications, we might get misleading, you know, the numerics might, well, yeah, it depends. Like, is that 1,000 time steps reasonable or not? Yeah. Okay. Well, I think I'll stop there. So the summary, we motivated a need for an augmented phase plane for discrete planar systems. I introduced the augmented phase plane for the Volterra-like difference equation. I showed you this GUI that I hope people will try, though there might be some bugs, so let me know so we can update it, because we haven't really done anything with it for 2 years. So MATLAB has newer versions, and you do have to download the runtime from the MATLAB site, but it is free. So any suggestions or bugs, let me know. And so we did demonstrate how to use this on unbounded timescales. This is a paper that we have, a manuscript. We're hoping to put it on the archive any day now and submit it any day now. And we've been saying that for any day now for a year, because I gave this talk in Bedlovo, and but we both are very busy and have been doing other things. Okay, and so again, if you want to contact me, have any questions, you can see some of my publications on my publication site. I should thank NSERC for letting me come here. They paid my way, they've been paying my students, they paid Sabrina's salary, and happy birthday to Martin. I use first names because we're all friends here because of Martin. I can use, first names. Happy birthday and many, many happy returns. Thank you.
Does anyone have some question or comments?
What was the reason again? Was this numerical trouble? Or you don't know the reason?
Well, no, it's because it's left ends. And so, right, so the time scale, there's an infinite number of points, like till you get to one,
So she's trying to put in the computer the actual time scale.
Yeah, if you put in the computer and run it, right? Like if you run an ODE, you're discretizing, but you discretize equal time steps, and so you can get going. But here, the time step is getting smaller and smaller and smaller and smaller. So each time you iterate, it's smaller and smaller. You never get anywhere until you pass one, and then you start going the other one. But so it's because it's a left-end set. So, for example, if you redefined at, say, if you redefined it for some epsilon, you said, okay, it's continuous, then there would be no problem, right? You just, like an ODE. And you'd wonder, like, I mean, it's sort of weird because an ODE has infinitely many points, well, more, like it's continuous, right? Here, it's infinitely many points, but it's, but on a computer, it's weird, like, so how would you really, what is the right way to simulate something like this if it's a left-dense point on the way to the
I mean, that's the time scale, so we have to work with it.
Yeah.
You can use a different time scale.
You could, so the thing is, maybe this time, so this was just to show that, there could be something funny going on. In a real application, I doubt there would be such a time scale, so there's probably never to worry. But to be aware, if you happen to have a time scale that's left dense, you might, even though the theory might say something, on a computer,
computers do what computers do.
Other question? So let's thank Professor Gale again.
Now you are expected to
Feel much better now.
I need to get a drink real first.
My air conditioner in my room is broken.
It only works when your card's on the door.
No, it's not that. It's there's an error code on it. But I told the front desk and it seemed routine. So they're fixing it.
Yes, true. It's like that.
Take away the other.
For me.
Scratches were correct. Almost mowing my lawn. I see. I understand. Because usually if you have cats, they scratch you. If you have mosquitoes, you scratch your legs.
We just need the
Yes.
there has to
But
be
I
some
think
kind of.
that it's not
At
an
least gets disfratized, right? When you
Okay, this requires just let us.
disfratized.
I try to discriminate. But there are adult.
Well, when you plot a continuous function, it puts all the points in at once and shows you the images. But now you're trying to have it generate, so it's never going to get there by iterations. You just need to put it in, like put t minus a half, t plus a half, t. You have to tell it to evaluate
That's what we
it.
did. We did T, and it did T 1,000 of the points, and I got to 1 point R, which didn't get near the your point one, which didn't
You
get
have
near
to
the
approximate which is around the point.
yeah. So you need to do a T minus epsilon, say that it's continuous.
I like the idea.
Yeah, make a T minus epsilon, and then you do it like an equation to T.
What were you saying?
Yes. This one has to be recorded. It's autonomous, right? It's not autonomous, so it's, you can be, it's a different autonomous, different autonomous, right?
Do we know what she does? I do, but I don't know if I'm misremembering being
Okay, let's start the second talk of this afternoon. Now, Professor Lucian Popa will speak about A2 optimal filtering.
Oh, I always, maybe in this case, say that I know Professor Popa-Lucci for, I think, 10 years, 2016 maybe, if I remember.
Something like this.
In Derby we met, in Ukraine. No,
First time we met in Albania
in Alba Julia.
when we had that Dr. Honoris Causa ceremony.
Yeah,
Professor
Professor.
Agarwal, and it was that conference in Timisoara.
And then when many times back to Alba Julia, he even came to Rolla, so.
Yeah, thank you. Yeah, we know for some times. be fair, the exact title of my talk, I put it there only managed to optimal filtering, but should be extending for system ordered by jump, linear stochastic differential equation subject to additive and multiplicative wide nose perturbation and Markovian jumping. So this is exactly the correct title, and I could not put all there in the presentation, so I stopped optimal filtering. This presentation is from a book that I published with two of my collaborators. It's Professor Vasile Dragan from the Romanian Academy, Institute of Mathematics of the Romanian Academy, and Samir is from University of Nancy from France. Published last year in Springer. So, as I pointed out, this talk have behind the problem of the filtering estimation of remote signal generated by the dynamical system model that I pointed out before. Now, what's interesting, the metric used here is the classical H-Doig type norm setting, because this is the general and classical, the natural one that arrived for this kind of jump stochastic systems. Also, the dimension of the state space, the considered filter is not prefixed. And further, what we will show is that the dimension of the optimal filters are equal to the dimension of the system under consideration. And the corresponding filter gains of the optimal filters are constructed based on the stabilizing solution of an adequately defined system for a jump matrix linear differential equation with a quantified jump operator. Now, I cannot pass over the system that we consider and choose some small details, so I have to pass, but I will not start to read that. Well, this way it looks like the state space representation of our dynamical systems, where, let's say, relation 1, or its component, where x are the vectors of the state parameters, y are the measurements available at the instance time, now k, and z is the remote signal which must be estimated. Now, in this relation, we use some classical assumptions. W of t is a R1-dimensional standard linear process defined on a given probability space. WD is a sequence of R2-dimensional independent random vectors defined on the same probability space with zero mean and covariance, the identity covariance. Then we have eta, it's a homogeneous standard Markov process defined on the probability space pointed out before, taking value from a finite set multiplied by tilde with the transition semigroup and the elements of the generated matrix verify the relation to the components are positive and so should be with 0. W of d, W index d, and eta are equal independent stochastic processes. And further, for the additive disturbances, denoted by C and zeta index d, which are affecting the vector dynamical system, we assume stochastic processes which satisfies the following assumptions. So for C, we have that is an MC-dimensional linear process defined on the probability space. Property at 0 mean covariance, it's at tilde index C, S minus D. Then we have zeta index D is a sequence of M index C D dimensional dependent random vectors, having, as I pointed out, the 0 mean and the covariance. Here we have delta index D, where delta index D is a positive defined known matrix. And of course, W W, X, D, eta, Xi, and zeta and D are control independent stochastic processes. Regarding the matrices that are involved in our system, all of them are supposed to be known matrices. Now we have the original system, we have the assumptions that are taken into account, and now the aim is to find the state space representation of such a dynamical system in a filter which feed at its input, which with the measurement value y, provide at its inputs a signal Z index F, which is the best estimate of the remote signal Z of T. Now, further we consider this filter giving the state space representation from relation 3. And what should be said about this is the fact that the dimension, as pointed out in the last proposition, of this state space of the filter of the form P is not prefixed. Of course, the matrices are arbitrary matrices subject only to the condition that the corresponding jump stochastic linear differential equation correlation for its exponentially stable in mean square. I did not point it out the definition of exponentially stable because it's a classical one. Those who hold this should know in the stochastic framework. We denote the F tilde, the family of the admissible filters. Of course, we have the constraint that the corresponding jump stochastic linear differential equation of 4 should be exponentially stable in mean square. In this line, we extended the problem. We had a result in 2018, if I'm not wrong, and that was the first paper that extended this classical definition of exponential stability to the more general case of exponential dichotomy, and yeah, from my point of view, that is the first result. We didn't find any other result that extended this definition, and we found it somehow. Why? Because the guys who are working mainly with filtering programs are the engineers, not the mathematicians, and they are not familiar with that definition. It's not in any books up to PhD level for engineers. Yeah. Now, I will start from this point to construct slowly the main theorem of this presentation. Now, coupling the arbitrary admissible filter to the dynamical system G and taking u of k being equal with y of k hash, one obtains the following resulting system, denoted G and the CL. And in this system, we have the notations for the matrices which are involved. And now the quality of the estimation achieved by an admissible filter will be determined by the hash to norm of the corresponding resulting system. Here we have two norms. One hash to norms. One and one denoted by tilde. And why we have two? Because we proved that for the hash to norms are natural to be involved in jump stochastic systems. But we proved a dwell-time correspondence between these two norms. More precisely, the first one, this one, is smaller or equal with the tilde 1 if hash is between 0 and 1. So 0 smaller than hash, smaller or equal with 1, and the inequality became vice versa if h is bigger or equal with 1. So these two norms allowed us to reduce the perturbations done by the white nodes or components. I will not go further to point out how these norms are, but only at the end the exact formula for our filter component. Now further we shall derive the state space representation of our filter, G tilde, which achieves the best estimation of a signal Z. That means the admissible filter should satisfy the following optimal conditions, one for each norm that we consider. Now, further, the developments will be done under the following assumption. That means the jump stochastic linear differential equation 9 is exponentially stable in mean square, and this one is obtained from the original system taking these components being equal to 0. And as a first consequence of this assumption, we have this proposition that says that the filter from the family of admissible filters corresponding to that jump stochastic linear differential equation is exponentially stable in mean square. Further, also it's a particular case when the multiplicative white noise perturbation vanish in original systems, and taking into account the same assumptions 1, 2, and 3 for each admissible filter, the corresponding system, jump stochastic systems, is exponentially stable in square. Now, these two results allowed us to compute the value of the norm that we pointed out before. For both of them, for an admissible filter. Yeah. Now we take into account that the resulting system 5 is a jump linear stochastic system without the output involving the time in the discrete time. Based on this, we have two corollary under the previous assumption. For each admissible filter, we have the representation formula for our first norm, where this y tilde is the unique bounded on-air solution of the following forward generalized Lyapunov type linear differential equation, population 13. And here we have exactly the same representation for the second H2 norm. The only difference is from the ins here. Okay. In both 13 and 15, that P of T is the probability distribution of the random variable beta of T satisfying the relation 16, while delta index C and delta index D are the covariances matrices introduced in the assumption. Now, based on this proposition, we have that forward generalized Lyapunov jump linear differential equation 13 has a unique bounded solution, and this solution on the space of symmetric matrices is differentiable over each interval, F continuous, and what is more important, it's a periodic function, period H, and satisfies this sign condition. And exactly the same way we have the bounded and this one, as if I'm not wrong, is not. Yeah, has a unique bounded solution exactly the same way for the second norm. Now, involving the coefficients of the state space representation of the dynamical system G, we introduce the following forward forward generals in the unknown of type jump linear differential equation set 7e, and exactly the same way 8e, and this allowed us to say that this system has a unique boundary solution, and this solution is a periodic function of period h satisfying the sum relation, and exactly in the same way we have from the second norm. And here we have the difference. So if for the first norm we have a unique bounded solution, here is a unique solution, and for the second norm the solution is not bounded. Now we need the stabilizing solution, and for this, to obtain the state space representation of our filter G sigma, G tilde, which satisfies the optimality condition 7, we need the following forward jump matrix linear differential equation. Of course, with Riccati type jumping operator, and a globally defined solution. This one is called stabilizing solution if these matrices are invertible and the corresponding closed loop system combination 20 is exponentially stable in mean squared. Now, exactly in the same way, we have considered the following forward jump matrix linear differential equation with the Riccati type jumping operator for the second norm, and exactly the same way here we have the stabilizing solution if these matrices are invertible and the corresponding closed loop system from relation 23 in this case is exponentially stable in mean squared. Now, one corollary, and then we can pass to the main results. The forward jump MLE 19 and 22 have at most one boundary on air and stabilizing solution, which satisfy the sign condition of 25, relation 25, exactly in the same way we have for the second norm from relation 26, and these solutions are differentiable on each interval of this form, left continuous, each component, and moreover, these stabilizing solutions are periodic functions of period h satisfying this sign condition. Now, we have the main theorems which provide us the problem. Now, assuming that the assumptions 1, 2, and 3 are fulfilled, the forward jump jump matrix linear differential equation with Riccati type jumping operator 90 has a bounded on and stabilizing solution which satisfies the sign condition. Now, considering the filter G tilde having the dimension of the state space, and that's f equal to the original dimension n, and the state space representation given in relation 27. Based on this or under these conditions, the G tilde lies in the family of admissible filters and satisfies the optimality condition, and here we have the representation of our norm that pointed out, and for any admissible filter GF for arbitrary dimension and image that's f equal with 1 of its state space, and exactly the same way we have the main theorem for the second hash to norm that we introduced. Now, concluding remarks. I could add here some applications in field monitoring, but I passed that because it made me way too much to consider. But instead of this, I will point out two events. As Marty says, we know each other for, let's say, 10 years. I could not add all the pictures because I would make a presentations. Maybe the next one I will make a funny presentation only with photos and events and what we have done all over the world. But I have here the picture only from the last conference where we met, and I remember that Martin asked me, well, we'll wait me to the airport. Yes, Martin. How I can find you? Don't worry, I have the best solution. Not the optimal, the best solution. So I took a beer, instead the beer in my hand. It was no problem for Martin to find me there. Yeah, so this was 1 or 2 years ago.
Before Corona.
No, it was after. It was in Bucharest, Martin.
Yeah. But you have to tell them what this castle behind this.
Yeah, that one is the Bran Castle of well, we know it as the Dracula Castle. And of course we took some beer with us.
In case Dracula is there.
Exactly. So we could not go there without some beer. Yes. And this one is also was a nice event during the pandemic. I never told you the real story. So we had the first beer Zoom meeting, right? And after 1 week, we had another one, which was called emergency beer Zoom meeting. Yeah. Well, what was funny, not to the first one, but to the second one, the fact that, well, it was a pandemic, so we could not travel so easy into the town. So my wife went to shoppings, and I told my wife, okay, buy some beer for me, because I have a meeting. To solve some problems. And my wife took care of me and bought 2 boxes. But what she didn't tell me that she bought beer without alcohol. So in 3 or 4 hours, everybody was very, very happy, not me. So I never told this story to anybody. So in that moment,
And I didn't discover that?
no, nobody could. So everybody fall down and went went to sleep, but not me. I was so fresh even after 4 hours because I took a beer without alcohol.
So
Yes.
maybe tell who are these people? On the left, upper?
On the left, it's you. It's Thomas
Thomas Carvalho.
Caraballo.
Christian.
Christian.
Who is the next one?
It's Jacqueline.
Yeah.
And then on the right side, it's Ovidio.
Wait, the order. Who is next? Who is in the middle?
There.
That is the one speaking, you see.
Yeah, no, he's there. I'm looking here. Who's there?
That's me.
Maggie, yeah.
Yes,
Is that Alexandra?
It's Alexandro.
Yeah.
Here it's
Agnieszka?
Agnieszka, and here is Ovidio.
Ovidio.
But I took only 1 page. There were more.
There were more, yeah.
I think this is from the first and this is from the second. Yes, yeah. Not so happy there.
And I think we had every 2 weeks or so.
I don't know exactly. But I also remember that it was your birthday, and I write him an email. Martin, happy birthday, something like this. I realized it was in Romania. It was 7 o'clock in the morning. Martin said, "Well, it's 11 o'clock here. We still have 1 hour to celebrate." Okay, and we start to celebrate, and at 8 o'clock he said, me instead going to the university. I went back.
And you didn't have the non-alcoholic.
No, it was with alcohol. So at 8 o'clock, instead going to the university, I went back to sleep. Okay. Thank you. Bye.
Questions?
Yeah.
Yeah, I noticed that early on you had a prescribed exponential stability.
You speak about the exponential stability definition.
Yeah. Is that prescribed in such a way that you, with knowledge of what jumps are going to be in your process, or is you're just making it big enough to keep whatever jumps are bounded?
Exactly the second part.
Okay. But do you have knowledge of how big those jumps could be, and the Q is picked big enough to?
Well, the idea is to choose that components beta and alpha such that the how to call it? Yeah, I got your point. How you speak about the jumps?
Yeah.
Well, all the time we take into account that between that hk and hash plus 1k to have and to remain between that bound.
Yeah.
So it's a mandatory condition.
But Q is not a function of.
No.
Okay.
No.
Other question? So let's thank Lieutenant.
I can show you exactly how.
Yeah, it's interesting because there's something strange going on with top skills that's similar to this. In terms of rotation,
Yeah.
but it's also in terms of
Yeah, I got it.
so for a project that at some point
We have one more call after that.
where we do a prescribed I think alpha beta now, but it's not in terms
Of the data.
so similar things because you're putting that on there so you have your filter bins.
Converging. So it's mandatory.
Yeah, but I didn't know if you had some knowledge of the journey to begin with, or you just pick it big enough that it just.
Well, we just choose that big enough so that the convergence should be satisfied. We never look forward how big we can choose that. You got it. So we should have beta bigger or equal with 1 and alpha bigger than 0.
Yeah.
So we took them as a
Yeah, and you're not doing Markov operation systems, you're just doing
Well, I did not. There are some constraints that we consider. You need to take just put here some results without making smooth
Do
correlations.
you have simulations for this?
Yes, we have.
Okay, because I was one of the reasons why I'm asking is that you were using the Markov.
I can show you. We have in the
Yeah, those are hard to simulate.
Yeah, no, we have in field monitoring. It's a classical program for engineers. I don't know if you are familiar with field monitoring.
So you have.
Probably by a different name, but if you show me something that's got.
I can show you in the
Okay.
It's a classical program and where we consider all these components, but
Very neat.
reducing some details.
Yeah.
If you write in million letters, okay, forward you the
Something about is that legit? It was legit?
Oh, yeah, they did that for
No, it was just a fundraiser. But
You don't have an old program.
Yes.
I should still work on it.
Yeah.
Not helpful. I've been using my last for 20 years. And then they totally change it.
Right.
It's not helpful.
They don't care about you.
See, that thing so that thing by maybe there's some bet you're making $10. Guess the score, cut. But no one won, so we got all of it.
People who've been paying
No, it's completely legit. They played incorrectly.
It's like what happened to us. What happened to us?
Marcia Federson.
Who did the picture?
Probably checked.
Oh, but it wasn't you putting it in. Which one? This one? Yeah.
Oh, yeah. Martin.
I didn't.
He's
I'm looking for you.
because he's talking.
Are we starting?
Yeah, let's start. Now, Professor Marcelo Cavalcanti is talking about from linear to nonlinear, a resolvent criterion for polynomial stability of some group generated by monotony operators.
And of course, I also want to say something about my friend Marcelo. We met several times, I think 2 or 3 times in Sao Carlos, and well, once we were the whole night. You remember that somewhere? And last time also we had many beers together. So thanks.
Thank you very much. So, it's a pleasure, first of all, like to... can you hear me? More or less. Hello. So, first of all, I'd like to thank the organizers for this kind invitation. It's a pleasure to be here in the year of my 70th, commemorating year 60s. So, it's amazing for me. And I would like to ask the audience to deliver 2 slides in honor to Martin, okay? The first one is very formal. You are here at Unicamp to celebrate the 60th birthday of a giant of our field, Professor Martin Bohner. To speak about Martin, to speak about the structural impact. When we look at the landscape of modern mathematics, especially the beautiful universe for dynamic equations on time scales, differential equations and their application, Martin's footprints are everywhere. Everyone can see this. His work doesn't just accumulate thousands of citations. It acts as a foundation bridge that unifies continuous and discrete analysis into a single elegant language. But beyond the impressive mathematical, his age index, and the massive global impact of his papers, what truly defines Martin is his extraordinary spirit of collaboration. You can see everywhere this. He has built a worldwide network of co-authors, mentioning generations of mathematicians that turn research into a shared human journey. Martin, your scientific generosity has shaped our community deeply, and it's a privilege to honor you today. Not so formal. Now, one more personal note looking back to our history. Our mathematical paths crossed many times, especially during the legendary summer meeting at São Carlos, as you mentioned. And as you know, intense mathematical discussions required an equality in things about thermodynamic balance. So Martin, looking at you today, so sharp, wonderful, elegant, and energetic at 16, I have reached a definitive mathematical conclusion. All those uncomfortable glasses of beer we shared over these years in São Carlos were not just as for celebration, they were actually highly efficient non-linear time-scale regularization that keeps you permanently young. Happy 60th birthday, my dear friend. May your equations remain dynamic, your coefficients remain strictly positive, and may you share many more regularization beers in many other years to come in the future. Happy birthday.
Thank you.
That's why did I decide to do this? Because I don't have photos. I saw Valeria. No, I have several photos with Martin Bohner that disappeared. I wrote to everyone to have a photo. Jacqueline sent me photos, but I was hidden. In the video. No, any place in the tables. And so no photo and no interest in joking to comment today. Okay, now I would like to talk to you about a problem that I am investigating. So if you consider, for instance, I consider the wave equation that I prefer the wave, then, can you hear me? I prefer the wave equation than for instance, I can consider who has created this model. Duration bounded conditions, for instance, initial data. So the expectative is the following. Sometimes the initial model was not for the wave equation. There's a toy model to me. The initial model is for the mathematician, like plates, flight structures. This model for with the non-local damping has been introduced by mathematician Taylor during the decentralization paper to NASA, United States. What they interesting, and sometimes they consider for the flight equation, they consider the kinetic, the energy associated to for the wave equations. In my case, is given by this. Okay. So, observe. You have a damping such that who drives the damping can be the potential energy or the kinetic part, or the total energy. So you have three possibilities. So I would like to show you about this. How this lack of damping, no local damping, produces not a fast decay but a slow decay. Okay? Here is the model. When my function A has an M here that is strictly positive, there's nothing to do because my friction is very hard. So it produces a very fast decay, exponential decay. But if I allow the capital M degenerates, you have problems like this. Okay? So, as I mentioned about accretion data, and they create this model, here are the possibilities, or potential, or kinetic, or the total energy here. Okay, this is the energy, the weak energy. This is the a regular energy, you see that it's easy. If you multiply this equation formally by ut, you obtain the first one. If you are in a bounded set, you multiply by minus Laplacian of ut, you obtain a strong energy. But what good in this model is that both energy are dissipatives. So they no matter you consider A1 like a potential, the kinetic or the total energy, I have both the regular energy and the weak energy non-increasing. Okay? So in one paper that I, with my wife Valeria Cavalcanti and other colleagues, we obtained two scenarios doing a lot of computations using Unakal method or Comunique method, very well known methods in literature. In the case, my dissipation is solely the gradient is different than the temporal velocity. In this case, you obtain one square root of I put here. For this kind of dissipation, the decay, you can see, is like this. When I change the potential energy to the kinetic part or the total energy, you obtain the fast decay, the best decay. I can ask you, why best? Because the following. So, my energy decreasing to now can be positive or zero. But positive cannot. Okay, positive would imply exponential decay. No chance. Because my energy is bounded by 1 over t. That's why 1 over t is the sharpest decay to this kind of model. What's going on? The function that governs the damping, drives the damping, is not, like, for instance, I give you an example. Almost passed my life studying the wave equation plus not a temporal but a spatial according to well-known hypothesis of Jacques Lillon. You put an observer, his eye, the observer sees a domain when I have tangents, and what to do? You get an open set around this boundary, and this is enough for stabilizing or stop the system according to. So the dissipation when you have this is not easy to prove in general, because even in the linear setting. So this was discovered in the 70s, 80s by Jacques Lillon and his equipe in France. But when you combine the position and time, you have a big problem. So I was in my mind, how can I control this? How can I create a method or develop a method that works well, but and escape? Because my dream was to consider the Borishev-Tomilov. This is amazing paper. And to employ this, you get your equation, you get your matrix, your operator, linear, unfortunately linear, and you look to the resolvent operator. But if you look at this, the semi-group, the case like this. So my idea is that the physical intuition or resonance or lack of coercivity at the low frequency remains. I'll show you. So my proposal, this paper is me, Valéria, and Jaime Rivera, is instead of to consider the T, the lambda going to infinite, to on the current to consider lambda conversion to zero. It is works. So you have to get the spectral equation associated to our problem. You have an operator. This is now in terms of this non-linear semigroup, not linear semigroup anymore. So as I told you, the main thesis is to see the singular behavior of the resolvent near zero. What you call a non-linear Tauberian principle. So I have this question in my mind a long time. But last year, given a course with my PhD students of non-linear semigroup, I realized that when I saw the UCIT and the Crandall-Liggett formula, so that it could be worked. Just connecting the linear case, if you come back to the linear case, close to zero, you obtain this kind of decay, where alpha is associated to the coercivity of the linear operator, for instance. But as I mentioned a few minutes ago, one question. If you have kinetic, we have the best decay. Total energy, the best decay. But the potential energy, though, with this new Tauberian, you also have a nice decay 1 over T, even if you localize it in X. So I will show the idea. I will consider from now on an operator, a nonlinear operator, and the resolvent in its general formula. And this is the linear backmap for the linear case. This is now in tension. So we propose to capture this information, use the real resolvent equation near the orange. This is, I recall the homogeneity of an operator that will produce some coercivity in my equation, for instance, think like this. And I will recall this. When during the seminar, maybe I will go to the Martin, your area, in order to prove something like this. Not in your area, but like a strategy. So assume that I have some kind of coercivity. And the resolvent near the orange it has a blow up, a roof like this when lambda goes to 0. So I have two exponents, 2 powers. P represents the coercivity that eventually comes from the homogeneity, and beta corresponds to the roof of the resolvent near zero, not infinite. If these two hypotheses hold, the nonlinear semigroup decays when in this rate, where P is associated to the homogeneity, coercivity, and beta is the explosion of the resolvent near zero. And the proof of this theorem is very delicate. I will show 4 slides to give the more or less the idea. So I first have to discuss the spatial recurrence like this. In a second step, I will combine the coercivity and the explosion of my resolvent near the orange, and finally I obtain this expression. I skip several steps, of course, that will give you this because of this formula. So I found this interesting, and I will show you, because this is very, the cut down issue, the result is very, very, very strong. It's very, very, very strong. And you say, Tomilov, Borishev, Bruce, Gear, you forget these guys. Once when my collaborator James said, does it just exist just to prove nonlinear existence of nonlinear semigroups? No. I will find in the future some interesting thing about this. It's impossible. Grandal, Richer, Gato, and so on. Hey guys, resist. Okay, this model, when I have velocity and velocity, you have the wave equation. Consider the wave for simplicity, but the wave plate is the same. One important thing, this Simon group must exist. For this, I need to prove first what? Solutions. Regular, sometimes I will also to prove just regular solutions in other weak solutions. For instance, if you see this model, you can multiply in a bounded domain, but ut minus ut, eight functions of minus Laplacian, deletion, boundary conditions, you obtain two nice estimates. But if you use a Galecki, for instance, you have to pass to the limit in the energy. You have a problem. If you try to use a non-linear semigroup, you have to consider your operator maximum monotone or omega creative, and so on. So, the result is correct only if the existence exists. Okay? And sometimes the result is correct for regular solutions, just. It's impossible to go for regular solutions for 2x solutions by density. Sometimes it happens. In this case, it remains that just regular solutions decay in a determined rate. So the energy space, and you obtain the resolvent equation. I will go faster here because now it's coffee break. And the idea is to obtain some structure like this. observe that when I multiply this equation by L, I obtain this one. When this guarantees that close to zero, V is bounded. The gradient of V, the gradient is, I'm talking about the regular solutions. So by Poincaré, V. Sometimes you cannot escape for gradient. Okay? And once you have this for V, you have the same for U. Done. So you can walk back to the formula. I will show. If I consider the same, here's a mere generalization, sorry. When you consider a nonlinear rule. In this case, what changed? The idea is the same. You obtain this. And at the end, this implies the growth of the resultant, 1 over t, in both cases. But when you see the homogeneity is 2 gamma plus 1, it comes from the hypothesis here. And at the end, combine everything, you obtain this polynomial indifferent decay. So the formula is this one. This beta is how the resolvent blows up, with the roof of the resolvent. And P comes from the homogeneity or coercivity of the operator. In the first case, my M is 1, so the case sharp. In the second case, I put a nonlinear damping, I have a worse decay. And so on. This mode is the same, velocity, but and the same, I will not annul. In even this case, you obtain the same scheme. So here you can see, nobody consider A special, local. I have this, using this nonlinear operator. For Kirchhoff modus, the total energy, Kelvin void. The more interesting this is that when you use Nakao method, for example, Comunic method. In Comunic method, you have to prove that the proper integral of square of the energy must be bounded by the energy in S, eventually a constant that depends S. Or Nakao is equivalent. If you try to do this, but this guy, you are not able to prove this. Using the computations, usual computations, you prove that the square is just finite point. So you have to do a trick, the 1 plus t the square derivative of this in order to obtain a 1 of square root of t. So the final remark, does it work just up to models like non-local? No. This work is not finished. You are investigating. I will skip this. Yes. If you consider, for instance, this relationship between beta and B, for instance. And you can divide, or if you get beta less student than 1, you can obtain, for instance, something like this, if you consider, if you are able to prove this. In case you obtain something p between 1 and 2, you can find very fast decay, 1, 2, and so on. I give you examples for the molasses system. This confers with the literature. The decay will be like this. The usual damping, we select 3/2, and the decay will be like this. For this model with P here, the decay is like this. And so on. So, and finally, if in case my operator is non-linear, this operator is wonderful with elliptic equations, is wonderful for parabolic equations, it's terrible for hyperbolic equations. The existence of evolutions is an open problem if you drop this guy. Without minus Laplacian of t, you don't have existence until now, as far as I know. That's risk. A lot of people are looking for this strongly. But with this, everyone believes. But in this case, because if you consider parabolic, it's not to do. Like an ODE. In this case, not getting the computation, you obtain this optimal decay rate associated to this kind of law. In fact, this rate was obtained by Matofu and Wansorian that a long time ago, they put a non-linearity like exponential of u squared. And they used in Trudick-Moser. But the problem was in Matofu, they proved that when P is 2, the Laplacian, they have exponential decay. And it's different, the same decay, for a semi-linear, for a non-linear, two times non-linear problem. With a same, you should say, people of the attractor, I must say if I put FU here, amen. If you put FU here, and if you use traditional methods, forget. The attractor will be trivial. Well behavior F. So, I think this is. Thank you very much. Get in the Facebook.
Yeah.
Questions?
No, I don't. I mean, now that I have one of the main experts here, I want to ask you something that I always wonder. You know, here in this equation, t, yeah, is in R, and the x is from some omega and so on. I mean, there must be a lot of stuff, well, probably not, but what about when t is integer? There should be something done. How much is done?
Yeah, there are a lot of things to do this.
But did you ever work on anything like that?
No.
No. Because then also t can be eventually in a time scale.
Yes.
But this seems to be too far. I mean, that seems a big project. We will probably not see that in a long time. Yeah.
In this particular case, in this version.
Not just this equation. I mean, many such equations. Yeah. many such problems.
So the central idea is to see the resolvent near the origin, like a real, you don't have imaginary X. And the coercivity. If you drop the resolvent decay, if you consider able to prove any kind of if you have the coercivity inequality, maybe you have just with give you decay, but not the best one.
Yeah.
Just the coercivity gives decay, but not the best one. You have to look at the coercivity, homogeneity, and also the growth or the explosion. Near zero. This is the idea I would like to say to you.
So, and then another question, how about when you replace these derivatives, let's say the time derivative by a fractional derivative? Did you do any work with that?
No. This should be certainly terrible. Ooh. If you put a fractional derivative, forget this, just a fractional derivative is no local in time. The decay will not be exponential, just polynomial. If you put two non-local terms fighting each other, the worst scenario.
That's the worst.
Yeah. But it's an interesting to consider.
Other question? Not, let's thank Professor Marcelo again. Now is the call.
Maybe just a long
So now I'd like to introduce Tom Kuchet, that he speak about oscillation of time-varying parameter class of hypergeometric functions.
Yeah, and Tom is my PhD student, the first one who came from Marshall University.
No, second.
The second one. And then he went not back to Marshall University, but somewhere else, and then back to Marshall University. So that's where he started. You know, he returned there. And yeah, so this is a very nice university. I went there many times, and I'm looking forward also to receive now more students, Tom students, so we can continue this tradition. And yeah, so.
Thank you. Happy to be here, happy to organize, happy that you came. I did my undergraduate here and I worked with Bonita Lawrence, some of you know her. And it's because of her that I met Martin, and the rest is history. And she didn't prepare me for who he is, but she knew our personalities would match, and so it worked out very well. So I'm from West Virginia. It's a picture of a beautiful place, my favorite place in the state. It's called Dolly Sans. It's a piece of because of the ice age that happened, the ice recedes, and the elevation of this place keeps the plant life somewhat arctic. There's some Canadian plants you don't find anywhere else except up in North Canada in this place. So it's beautiful. So there's my advertisement to come to West Virginia. But also, This is the earliest picture I can find of myself with Martin. Somehow I was in Rolla for 3 years and we didn't take pictures. Maybe one exists, but I couldn't find it. So this was in celebration of his daughter's first birthday, Yasmin's birthday. Let's see, Sabrina's there. My wife now. She wasn't my wife at the time. I think that's Mazen.
Which way is your?
Yeah, that's
You don't see from the face, only from the shape.
I've had the beard since I got married. So if I ever shave it, my children will cry. Okay, so then 2015 I graduated. Sabrina was also already graduated. I graduated 1 semester after her. And I'll never forget this day, not because I graduated, but because I had to sit in the ceremony with food poisoning. You know, they give these long speeches and boring, and I'm just trying not to throw up. And,
But you're smiling.
it's a forced smile. You can tell it's forced. Okay, and then 2016 was his 50th birthday celebration. His wife organized this at the public house, and I know pictures of it exist, but I couldn't find them. So you have the flyer that was made to celebrate. So 10 years ago, this was it. Now we're here. We'll see what happens in the next 10. So after I graduated, I went to my first position, and I went to the Iktia in Timisoara. So this is a picture from the excursion there. We went to a winery, Rekash, I think it was called. And it was good, great conference. This was my first time in Brazil. Sabrina was also there, but she took the picture. You can ask us the story of this later. 2019, Lisbon. I had no pictures, but there was a video of the Gambe, so I screenshotted it for this. And this guy was not a mathematician. I think he was from Canada or something, and he just met us. Then COVID happened, and there were many of such things. This is from the Poland. We were planning to go to Poland for the conference, but no one wanted to travel. And Martin's somehow still in the ice house somehow. How he managed this. He teleported to Poland from his room. Okay, then that was this. I don't know, maybe we didn't meet in 2023, but 2024, Paris. 2025, Martin visited me in Huntington. This is my student, he's right there. There's Martin, there's Bonnie Lawrence, there's me, and Clayton Brooks took the picture, if you know him. Okay, so if I was wiser, I would have took a picture yesterday as the next slide, but I forgot. Okay, so the title of this talk sounds nothing like timescales, but I promise it's leading somewhere. I got to give you some background first. So these hypergeometric functions are a power series made with these Pockhammer symbols. They're kind of a rising factorial. They are a ratio of certain gamma functions. And the idea of hypergeometric series is if your coefficient function to your variable is a rational function of the index, then probably you can write it as such a function. I'll use this estimate later. It's an old gamma function estimate. So these functions are very old. They go back to Euler and Gauss. So here is a picture of an 1801 thing that Euler wrote where he was talking about this series, and he arrived at the differential equation for it. I like seeing these old things because the notation is somewhat interesting. So we're going to be doing not this, that's continuous, we'll be doing discrete. And the purpose of this talk, the title, so time-varying parameter, the discrete will give us this time-varying parameter, as you'll see. So I'll give you the general definition in a moment, but I'm just setting some history for you here. Okay, Gauss also studied these functions. He put symbols in his title. The purpose of these hypergeometric functions is that they're kind of a library of functions. Pretty much every function you run into as an undergraduate, early graduate student, can be found by choosing certain parameters of these functions to get to get your function. So you see sines and cosines, you see exponentials, even more complicated things, orthogonal Laguerre, Hermite, Legendre polynomials, all these things you've probably used or heard of are examples of this type of function. And it's only the 2f1 that gives all of these. You'll see in a moment that you can have as many subscripts as you can. The subscripts can be any integer you want, any non-negative integer you want, and so you can imagine how enormous the list becomes. These functions are crucial in computer algebra systems. If you've ever used Mathematica, sometimes it spits out a hypergeometric PFQ. That's what these guys are. So what are they in general? So we have two subscripts sort of in the name of the function, and those can be non-negative integers. And I think of the P as counting how many top factors I have, and the Q is counting how many bottom factors. So there's P factors of the A's on the top, there's Q of the B's on the bottom, and we have the standard Taylor monomial attached to it. Okay, you can do simple calculus and understand convergence and divergence of these things, which for us isn't super important. But I guess you can think of the Pockhammer symbols, they're essentially, they grow like factorials. So if you have the one factorial here already, and then each of the BKs is a factorial, each of the AKs is somewhat of a factorial, and so this analysis is trivial. All right, the hypergeometric functions. So when I do discrete, I will use a Latin F, a regular F. When I'm using continuous, I'm using the script F. That's how I'm going to distinguish them as we move forward. So these classical hypergeometric functions have a factored differential equation. It looks something like this when you do the one that Euler did. So this theta operator is a t and a derivative. And you can see if you expand this out very carefully, it will turn into this equation here. Okay, so I show you this because we'll have the same in the discrete case. Okay, so how do we get the discrete ones? So my dissertation with Martin, when I got to Rolla, I walked to Martin the first day. I said, hi, I was sent by Bonita. And he said, great, read this paper. It was something about Nicholson blowflies or something, some biomath, and I read it. I didn't like it that much, so he sent me some other things. I eventually took a summer class on special functions, and I loved it. And so the next, it was a summer class, so Martin was traveling. So when he came back finally in August, I told him, this is what I'm going to do. And he said, okay. And so this discrete thing here is pretty much most of what I did my dissertation work on, and it's paid off a lot since then, various ways, including today. So the main idea is we have our hypergeometric series. You saw on the slide about Gauss that sometimes they'll put like a negative or a 1/4 as a factor there, and sometimes you get like a t squared as an input. And so I need to be able to track this c and the n on there. Now I want a discrete power series, so I want to use the falling powers. T minus 1, T minus 2, and if I don't track the n and the c separately, I cannot plug them in all together. So these three parameters are just giving me the ability to mimic everything going on in that argument. So we pick an n, we pick a c, and in the a's and b's, and we have our function. Now, we wrote a paper in 2018 where we explored this series, and we found the difference equation version of that formula. So some differences of this theta operator. Before it was t times the derivative. Now it's t times a shift minus 1 as an operator times the derivative, the difference. And when you use that, you get this expression. Now it's a little more complicated than the continuous case. Well, discrete's more complicated already, but the n has to be tracked, and so that's included. The c is not in the earlier slide, so it's also tracked. And this theta operator has this 1 over n on it that also comes along. So if we do the Euler case, p equal 2, q equal 1, n equal 1, it turns into this expression. And then again, you play the normal game. You multiply on the right by the y, you multiply things out, product rule, blah, 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 and you arrive at this difference equation. And from there, you can take it in some different directions. What I'm going to do is I'm going to take these difference equations that pop out of this formula, and I'm going to look only at the ones that are second order, and then I'm going to try to understand the oscillation theory of them. Now why? Who cares? Okay, oscillation, great, but these things directly connect to the classical case. So if I prove oscillation for these discrete guys, then I automatically obtain an oscillation type result for the continuous ones. And that's the main idea here. So how does this work? So if I have this classical series, the discrete one has the falling power over here. So this formula writes the falling power in terms of these Pockhammer symbols. Those are these factors out here. So if I have n Pockhammer symbols, then I have n more factors on the top, which means my subscript becomes p plus n. Okay. So the time in the title it says time varying coefficients, and by that I mean the continuous hypergeometric. The t variable is in the top parameters. So okay. So you think all the big list of the functions that these things encode, and then we have the ability to do the discrete in this connection. So some oscillation results might tell us something interesting about some function we've heard of before. That's the idea. Okay, so the trivial case, if I have 0f0, so what that means is I have no Pockhammer symbols on top, no Pockhammer symbols on the bottom, and therefore I only have this series. Okay, people in timescales know this series converges to the discrete exponential, which has a nice explosive formula. So you ask, okay, where is this thing oscillating? Clearly, if Cassie is less than -1, it's oscillating, otherwise not.
Okay.
And so, because we get oscillation of the discrete 0f0, we get this oscillation result for the continuous 1f0 for free. So I usually am thinking of the discrete variable t as an integer, but if you prove the integer oscillates, then the continuous version also must, because it must go through the same points. Okay, so some examples of this discrete special function. So after I left Rolla and got my position, I was made papers out with students and myself and some colleagues, various kinds. Like I wrote a Bessel with Martin. These three are from the Green Book. I wrote this one, these with students. This one's a collaborator in the Middle East. And so I was sort of just building up the library of functions, proving properties of them, blah, blah, blah. Okay, so we want to talk about oscillation and non-oscillation. So let's start with oscillation. So I think Roman's talk, he was talking about this formula, and maybe many others. So this is our discrete Sturm-Liouville form with the sigma on it, on the y. So in the Green Book, Martin's book, you get this nice theorem. If you put the function into this form, you have the coefficients p and q. You check these series for convergence or not. And if they both diverge to positive infinity, then you get that the difference equation is oscillatory, which means every solution is oscillatory. So we know difference equations that these discrete things solve. So that's the goal. So which ones do we care about? So this is the difference equation for the general PFQ. So you think about what the order would be. Every theta gives you a new difference. So, okay, the q, this q must be less than or equal to 1, because if this q was 2, you'd have this theta, and then 2 more, suddenly you're third order, okay? So we have that restriction on q. P must be less than or equal to 2 because of this p here for the same reason. But this shift here maybe causes problems. And when I say second order, I mean second order linear, A0 times delta ny plus a1 delta n minus 1y. No shifts in the arguments, okay? So it turns out this row affects that when you work on it, so there's an extra condition here. This leads to this list of functions. And I will not do them all today because this is ongoing research. I got a grant in August to work on this problem and a few others. One of the other ones my student will talk about on Friday. So I'm still in the middle of this, so it's a preliminary report. But I know many people here know the oscillation theory for higher order, and I don't. So please tell me about it. Maybe I need to talk to Roman. Okay, so we're going to look at just two of these. But first, a trivial case. So these functions have a parameter Cassi in them, and it just acts as a geometric factor. So if Cassi is 0, then what happens? Well, every term in this sum is 0 all the time. It's identically 1. Doesn't oscillate. Okay, boring. We don't need discrete oscillation theory or anything like that to make this deduction. Okay. So let's look at 0f1. So if I take the difference equation for 0f1, I put in the definition of the theta, t rho delta. I expand it out, I get this expression. That's having the shifts in the arguments. So I divide one of the t's off, I replace t with t plus 2, and I have this very nice equation. Okay, I have plus 1s here because of this theorem. So in Martin's book, if you put a difference equation in this form, then you can immediately find the p and the q for the Sturm-Liouville form, and it's straightforward. So we do that. We take this equation that we just got. We find the f and the g. We find the p and the q. And so this difference equation, for the Leighton-Wintner theorem, I need to check, does the reciprocal of this could diverge? And does the sum of this also diverge? And so we look at 1 over pk. We get this ratio, and on the early slide, I pointed out this old result from the 50s about ratios of gamma functions. And so using that result, this sum, it's not starting at 0 anymore, but as k gets big, it's essentially a sum of this type. And okay, we get this result for where it converges. So if b is less than or equal to 1, we'll get the diverging. Great. So we could get oscillation here, but we also have to check this sum. If you do the same kind of argument, you arrive here, and you get divergence when b is positive. So we do need this coefficient to be positive because the Leighton-Wintner theorem requires the sum to go to plus infinity. So to summarize these results, if b is less than or equal to 1 and this thing is positive, then great. If b is greater than 1 and this thing is positive, then great. So we arrive at this result. Oh, I should have mentioned, I'm collaborating on this with Nick, who's sitting over there, and Ozcan in Turkey. All right. So what we get in the parameter space, because in this function I only have Cassi and b as parameters, so I have a plane of possibilities. Cassi equals 0 is ruled out by the trivial case. And this result shows if my parameters come from this little rectangle going off to minus infinity, then the function oscillates. Outside of this region, we don't know yet. Okay, this is the first one we got that was oscillating, and we're still working, but this is the main idea that I'm trying to push and get all the second order. Okay, so this 0f1 discrete, by the connection to the continuous case, is a 1f1 with this time-varying parameter. And if you look in the literature, you'll find that these are associated Laguerre polynomials. And so because 1f1 is this type of function, we know the 1f1 is the discrete one we just looked at, we conclude that this sequence is oscillating. This sequence of Laguerre polynomials evaluated at a certain value oscillates. And probably this is known somewhere, but I thought it's a neat connection. And it's the kind of thing I'm trying to find good examples of as I do this. So there's an application, I guess. Okay, that's all I have to say for oscillation. I don't have other oscillations yet, but again, it's a work in progress. Okay, so for non-oscillation, it was much more difficult to do this. So I reverted to the discrete oscillation theory book that Martin was a co-author on. And it's this theorem in particular that ended up being pretty useful for this result. So we get a second different type of a Sturm-Liouville form here. So we have to, again, start with the difference equation for the hypergeometric, put it into now this form, figure out the C tilde and the B tilde, do the comparison, and see what happens. Okay, it's very straightforward. It's just very tedious algebra. So if I look at 1f0, discrete 1f0, it solves this difference equation. When I simplify, I do the, divide by t and replace t with t plus 2, whatever that was. And then I use simple useful formula sometimes. I can put it again into that same form from the timescales book. And then I use that theorem again to get the p and the q for the classical Sturm-Liouville form. Now I could maybe try to go directly to the other form, but I took this way because it works pretty straightforward. So now I have the original Sturm-Liouville form, but that's not the one I need for this theorem. So I need a step to get this C tilde and the B tilde. Okay, not difficult. It turns out when you compare the two equations, this one and the other Sturm-Liouville form, you can find the C tilde and the B tilde have certain forms, and okay, this is the form, so I'm not proving that right now. And so ultimately I get the C tilde looks like this, I get the B tilde looks like this, and so now the theorem says I have to show B tildes for sufficiently large t's bigger than the maximum of both of these. Okay, so I just check them one by one. So I have to check, is B tilde bigger than or equal to C tilde, t minus 1, okay? And when you reduce this inequality, you end up with this expression. Now, I didn't mention it, but there's a requirement here that I have to impose that the C is positive. Because in this book, when they introduced this formula, they put that the C is positive as a condition. So I am using that as a restriction right now to be conservative in the calculations. But I'll say some more about that at the end. So I have, again, this condition because C is positive. And with that, I can solve this inequality, and I arrive at a certain relationship between the two parameters of this function. And in this case, it looks like this. The other inequality just holds. The left-hand side is just a function of t, which is going to infinity. The right-hand side is exactly 4, so that one's always true. So this one gives no extra restriction. This one gives a restriction. And so this is our picture right now. Now, numerically, we've checked, every result we prove, it seems to work. But, sometimes you'll get non-oscillation out in this region, and which means that this theorem isn't going to give it to us, so we need a different theorem and so on, okay? So that book has 8 million theorems in it, and so we start going through one by one, checking that which ones are working, which ones not working. That's been our progress, job work the last few months. Okay, so we get this result, and the corollary for the continuous case is this. Now, if you know anything about hypergeometric, 2f0 is very divergent. Remember, the first subscript are your numerator sort of factorial-like factors. The 0 is your denominator factorial-like factors, and you have a 1 over k factorial in the sum always. So you essentially have a factorial squared divided by factorial. It's definitely divergent. But for discrete t, positive t, 1, 2, 3, 4, 5, the fact that this appears in the series as a Pockhammer symbol means the series will terminate. If I have minus 5 sub 3, that's minus 5, minus 4, minus 3 is not 0, but minus 5 sub 7, you'll eventually hit 0 and the whole thing will terminate all the time. So in this case, the discrete function exists. The continuous version only exists at the positive integers. So it's a continuous object, sort of, but it only exists at integers. I think I think there's a way to do a divergent series expansion for this, but okay, let's not get into that. So again, this was a preliminary report. That's the main idea I'm pursuing right now for my grant. So what's next? So, okay, clearly we have very limited understanding of the parameter spaces in my pictures. There's lots of white space. So we got to keep cracking at it and understanding. We've made some progress beyond what I've shown you, but not much. So I mentioned earlier this discrete oscillation theory book has this condition that the tilde C is positive. Well, okay, for us it's not always useful because, say for instance in this function, if I had C negative in this part of the plane, now this function's oscillating all the time. It's no longer positive. So we need to write some new theorems to take care of this. Some work we did only like 2 weeks ago is suggesting maybe a condition like this can be used and then mimic the proofs in that situation, and then we get the oscillation again. So maybe next time I'll talk about that. Again, it's a timescale session, so I should talk about timescales a little bit. So my main job in my dissertation was to do geometric series on timescales. Turned out it's a very difficult problem. To even define, defining them is okay, but finding dynamic equations for them is very difficult. In my thesis, I had a problem posed, essentially an open problem, to figure it out. And I haven't figured it out since in the last 10 years. But I now have a master's student working on this problem, and he'll speak on Friday. Now, I restricted my attention to first and second order equations. I don't know higher order Sturm-Liouville theory very well, so I'll have to study that and then return to the higher order, but I think I have enough on my plate with second order at the moment. Another idea is that these functions, in the most generality, allow complex parameters. And if you do this in the discrete case, I don't know a good source for discrete oscillation theory in the complex plane, because you would need the real and imaginary parts both to go to be a generalized zero at the same time. And I haven't found any good resource on that, but if you know any for complex oscillation, please tell me about it. Okay, so here's some references. There's the Bessel paper. That was our first paper. This is the paper that the discrete was defined in. This one is where that ratio came from. This is the discrete oscillation theory book and the timescales book. And thank you.
Questions?
Okay, so you have in your sum, you replace the t to the n, k, by t sub n k falling.
Yeah.
So I think it's pretty clear that.
Oh, the definition exists.
In the timescale space, you will do h and k.
K factorial.
No, okay. The k factorial will not be there, yeah. So
I had the definition of the series in my dissertation.
But the problem is
the dynamic equation for it is difficult to find.
Oh, okay.
Because you need the timescales analog of polynomial coefficient differential equations for any timescale, and multiplying by hk is not the right answer. So this problem, this is answering essentially the question: what is a good candidate for polynomial coefficient dynamic equations? And if it was solved in general, that would do it. We've only done it in a very restricted case at this point. But
I didn't say HK, HNK as a subject.
well, yeah, but I mean generally the HKs are the polynomials we use.
Yeah.
But you put HNK for the n, yeah.
And that's not working?
Not working for what? I mean, you get the series, but you don't get a dynamic equation.
So you're looking for a different definition?
I want the same definition, but I want to understand how to, say for instance, if I have this. One candidate for the timescales analog is this.
But then you have to insert some t minus 1 somewhere.
Yeah, and maybe a sigma or something. But as far as I know, there's no systematic way. If I have some polynomial here of any order, how do I go from here to here? Well, turns out that's not the right answer, at least as far as, I mean, you can certainly define that equation, but its solution is not these functions.
Yeah. So normally, okay, the 2 primes should be 2 deltas, no problem. The prime should be a delta, and the y should be a y. No, they are always t's. You can join them, but we don't need to. But there are always t's in there.
Yeah.
So now each t could be either a t or a t plus 1, or maybe t minus 1.
That's right.
Yeah.
But no matter how you do this, you don't get this series. That's the problem.
None of them will do it.
No. Not with the HKs as the stand-in for the polynomials. So it doesn't work that way. It's not as simple as picking the timescale polynomial as you're, just importing it or anything like that. It's more delicate than this.
Just because if you have a polynomial series type solution, if you substitute it, at the very end you have h2 times some series.
Yeah.
Which has polynomials, but the product of polynomials is out of polynomials.
Yeah, that's exactly right. When you're solving this type of equation, you use the series method to do it.
Yeah.
So you need the ability for things like t squared, sum, ak, tk. And I cannot mimic that with this formula either. So I want to be able to do something like this, and I have a possible candidate, but we're still working on it.
But you know that integral of product of 2 polynomials become a polynomial.
Yes. Yeah.
That is the key.
Yeah.
So okay, so
But I never got it to work. I knew this result, but I tried it and it never works out for me.
So
Someone smarter than me can do it.
hn times hm, the integral is
hn plus m.
plus 1.
Plus 1, yeah. That's true. But the big problem with that also might be, okay, I've tried this, it doesn't work for what I want to do. I know for sure.
Other questions? Not, let's take them again.
On what sense? Well, yeah, like for example, if you have h3, you multiply by h5 divided by h3, you get h5, right? But again, you have to also do it term by term. So there's no coefficient.
Just 10 minutes to
You can multiply by to raise the power by 1, right? No time function. So what I did in my thesis is made it
By the way, I didn't get this email.
expressing the operator in terms of the time variable.
The talk now, Professor Sanket Tikare will speak about stability of linear dynamic equation via Lyapunov functions.
Yes, I should say, Sanket and we know each other only for 6 years, in 2020, January, when I was in India. But he came to that conference just to meet me. He already knew about timescales, but since then he learned a lot and he became a rising star in India for timescales. So please keep up the good work.
Push the middle.
Yes. Yes. Thank you, Martin. First of all, I would like to thank the organizers of this workshop for giving me the opportunity to present my work in front of these experts. I know Martin from last several years. I heard his name during my PhD. My PhD topic was Henstock-Crusoe integral and its application to integral transform. During that time, I came across one of the paper, Henstock-Crusoe delta Nabla integral by Peterson and Thompson. And in that paper, several references were given, and I came across one of the book, the first book of Martin. And I go to library and search that book, and from that, I started following his work and all. That was in 2012. Then after completing my PhD, I was looking for job and all. So I spent 6-7 years to search a job and this. Then I was totally out of research work. Then in 2019, in the last, I come to know that Martin Bohner is coming to India. So then I thought that I should meet him and I should discuss with him something regarding timescale. And then in January 2020, I met Martin, and then I start working on timescale. And at every stage of my research work, he helped me a lot how to write mathematical papers, how to think, and what are the mistakes we should avoid and all. Thank you, Martin. And now let us come to this work. Today I will be talking on stability of linear dynamic equation via Lyapunov function. Here we investigate sufficient condition for stability, asymptotic stability, exponential stability, and instability of first order linear dynamic equation on time scale with the help of suitable Lyapunov function. So these results are useful for investigation of stability of problem involving both continuous and discrete data simultaneously. The outline of this talk is as follows. First, we'll discuss stability problem, then some auxiliary results, some of the stability definitions, then Lyapunov theorem, and based on that Lyapunov theorem, we provide some main results of this work, and then finally we provide some illustrative example to show the applicability of the result obtained. Of course, this work is based on my joint work with recent joint work with Martin Bohner, Jervin Zen Lobo from India, and Giriraj Methi from India. So recently we have submitted this revision. Okay, the stability problem. In this work, we are going to establish a stability result for the first order linear dynamic equation of this form with this initial condition. Here, t is a time scale which is unbounded, and t0 is a point from time scale which is greater than or equal to 0, and this x0 is a vector in Rn, and b, the function b is assumed to be bounded Rd continuous. And we put the assumption that P is regressive, RD continuous, and circle P is continuous. Here we are going to develop and adapt the existing Lyapunov stability technique to the linear dynamic equation 1. extending certain previously known result to timescale framework. For this, we are going to take the advantage of the equivalence of our linear dynamic equation with this integral equation, and we derive our main results. Then auxiliary result, here we are going to follow this definition, this alternative definition of delta derivative. This definition is taken from the paper by Ecker and Augur, Stability of Obada Dynamic System on Timescale with Initial Difference. Here, the delta derivative of the function x at point t is defined to be the limit of this quotient. Then we put a remark that the vector x from timescale to Rn is delta differentiable at point t, provided each component is delta differentiable at point t. Then we are going to use this theorem, which is taken from Bohner-Peterson's book. Then we have proved one lemma, that is the equivalence of this our linear dynamic equation with this integral equation. Then this next theorem provides the guarantee of the existence of unique solution if f is RD continuous function, and if there exists positive L such that this Lipschitz type condition holds, then the dynamic equation has exactly one solution. And this result we have proved. This was our first paper with Igor Centers, Martin and me. And this was published in the special issue, edited by Jacqueline and Martin.
And Igor is here.
Yeah, he's there. Okay, so here we are going to follow these notations. That is, C is taken as a family of continuous function from t0 infinity timescale interval to Rn, which is a Banach space coupled with this norm, SUP norm. Then BR, we denote it as open ball of radius R centered at the null element of C. And okay, stability definition. A function phi is said to be of class K, provided it is well defined, continuous, it is strictly increasing, and it is strictly increasing with this condition, that is phi of 0 is 0. Then positive definite function, an RD continuous function P from T to R is said to be positive definite, provided it is P0 is 0, and there exists a class K function phi such that phi of t is less than or equal to pt, and it is said to be, and the same function p is said to be non-negative provided it satisfies this condition. Then we come to positive semi-definite function. An RD continuous function p from t to r is said to be positive definite provided p of 0 is 0 and p of t is greater than or equal to 0 for all t, and similarly negative semi-definiteness. Then positive definite function q, an RD continuous function q from t cross Rn to r is said to be positive definite if q at t comma 0 is 0, this bold 0 is from Rn, and there exists a class k function phi again such that phi of norm c norm x is less equal q of tx for all t in timescale t, and x belongs to br. Then a positive semi-definite function, RD continuous function. It's very similar to one-dimensional case. Then we come to the stability definition. Dynamic equation 1 is said to be stable, provided that for given epsilon positive, there exists delta which depends on epsilon as well as t naught, the initial point t naught, such that whenever the initial condition x naught, norm of x naught is less than or equal to delta, then each solution x of the dynamic equation 1 exists and it satisfies this inequality for all t greater than or equal to t naught. Then next, the definition of asymptotic stability. The dynamic equation 1 is said to be asymptotically stable provided it is stable according to the previous definition, and there exists gamma which depends on t naught, which is positive, such that this limit as t tends to infinity of this tends to 0 whenever a norm of x is less than or equal to gamma. Then exponential stable. The dynamic equation 1 is said to be exponentially stable provided that there exists beta constant which depends on t naught, which is positive constant, such that this inequality holds for all t greater than or equal to t naught. Okay. Let us come to Lyapunov theorem. The theorem is like this. If there exists a function v, which is CRD1 function on t cross br, which is positive definite on this one, and whose delta derivative v delta is negative semi-definite, then the trivial solution of dynamic equation 1 is stable according to the definition 9, which is given previously. The proof follows as: since the function v is positive definite, we have a class k function phi such that this inequality holds, and this phi of epsilon is greater than 0 because epsilon is greater than 0. And also, since v is positive definite and its delta derivative exists, the limit of this is 0 as norm of x0 tends to 0. That is according to epsilon delta definition. For given epsilon 1 positive, there exists delta which depends on epsilon 1, delta epsilon 1 positive, such that whenever this holds, then we have v of t naught x naught is less than or equal to epsilon 1. Now if we set epsilon 1 as phi of epsilon, then v of t naught x naught is less than or equal to is less than phi of epsilon. And with our assumption that we have taken assumption that delta is non-negative, is negative semi-definite, then this gives us that the function v as a function of t is a non-increasing function of t, and therefore we have this inequality. That is, phi of norm of xt is less than or equal to phi of epsilon for all norm of x naught is less than or equal to delta. Since the function phi is of class k, so we have norm of xt less than epsilon for all norm of x naught is less than or equal to delta. And hence, according to the definition 9, the dynamic equation 1 is stable. Then our main result. Suppose the assumption 2 holds, that is assumption 2 is that the function p is RD continuous, regressive, and circle minus p is continuous, that is the 2. And we assume that the integral of sigma t to infinity of this is less than or equal to del dt, where dt is this quantity given in 7. Then the trivial solution of dynamic equation 1 is stable according to the definition 9. The proof is as follows. We define a function vt as v1 plus v2. Then the delta derivative of delta is v1 delta plus v2 delta. We take v1 as norm of xt and v2 as integral t naught to t g of t s delta s, where this function g is defined in this way. So here we observe that the addition of these two functions v1 and v2, it is a positive definite with class k function phi of x equal to x, that is, it is phi is an identity function. Here delta derivative of v1 is this one, and by using the definition of delta derivative and simple useful formula, we have this one. Delta derivative of v1 is this quantity. In fact, this can be obtained, the justification is given here. When the initial condition is 0, then that equivalent integral equation reduces to this one. And applying theorem 1, that is differentiating this integral equation with respect to t, so we have to differentiate under the integral sign with respect to t, and after that we get this equation 10. Then subsequently we have the delta derivative of v1 is less than or equal to mod pt times integral t0 to t of this quantity minus norm of xt dt, where again dt is given in this way. So again, in view of theorem 1, that is which gives us how to differentiate under the integral sign with respect to t, we have v2 delta t is integral t0 to t of this plus g sigma t comma t, where g delta t is denotes the derivative of g with respect to the first variable t. Now here g sigma t comma t is this one, then and it's a delta derivative with respect to t, that is respect to first variable, comes out to be this one. Using this one, this previous this identity, we got that v2 delta t is this one given in 13. Now from 11 and 13, the 9 becomes, 9 is this one, that is delta derivative of v, it becomes delta derivative of vt is less than or equal to norm of xt mod of pt times this one. And by using the inequality, we have assumed that this integral is less than or equal to this one, so it gives us that delta derivative of vt is less than or equal to 0. That gives us that vt is v delta is negative semi-definite, and according to theorem 12 we can conclude that the dynamic equation 1 is stable. Then the next result, in addition to the hypothesis of the previous result, if we assume one more thing, that is integral from t0 to t of this quantity with respect to u tends to infinity as t tends to infinity, where d is defined that limit, then the trivial solution of dynamic equation 1 is asymptotically stable in the sense of definition 10. Here is the proof that since we have assumed that all the hypotheses of theorem 13, from theorem 13 we can say that the dynamic equation is stable, and from the computation of the same theorem we have this inequality. Now we have to prove the dynamic equation is asymptotically stable. So suppose it is not asymptotically stable, then there exists a solution x of dynamic equation 1 such that norm of x is less than or equal to s for some s greater than or equal to 0, and the limit of this norm of xt as t tends to infinity is not equal to 0. Then what will happen? There will exist r greater than 0 such that this inequality will hold for all t belongs to time scale and t greater than or equal to t naught. Okay, then by fundamental theorem of calculus we have Vt equal to V of T naught plus integral T naught to T delta derivative of V at S integral of delta derivative of Vs with respect to S. Then using the terms we got that Vt equal to is less than or equal to this one, that is, and we have already taken the function phi as the identity function. So this norm of minus norm of x, we can take this as this one, and with this implies that as t tends to infinity, we have assumed that this integral tends to infinity. So therefore Vt is also tends to minus times infinity, that is it tends to minus infinity, and this is not possible because we have assumed that the function v is positively definite, and hence our assumption that this assumption this one is not correct, and we should have limit t tends to infinity, norm of xt tends to infinity, and this gives us that the dynamic equation 1 is asymptotically stable. Then based on that result we can have the corollary that we assume that integral sigma t to infinity of this is equal to dt minus t raised to alpha, where dt is again defined in 7. Then the trivial solution of dynamic equation 1 is asymptotically stable. This we can prove based on the previous result, previous theorem. Then let us come to the exponential stability of dynamic equation. So we assume that the hypothesis of theorem 13 is satisfied, and the E, which is supremum of E circle minus P t comma t naught, mod of E circle minus P t comma t naught is less than infinity, and M is positive number such that it is this integral t to infinity of this is less than or equal to M. Then the trivial solution of dynamic equation 1 is exponentially stable. Here what we do, we take the function v1 as this one and v2 is this one, then we define a Lyapunov function v as v1 plus v2, then the delta derivative is this one for all t greater than or equal to t naught, Then after performing the same calculation as we done in the theorem 12, we arrived that delta derivative of v is less than or equal to norm of xt minus e circle minus p t comma t naught x naught times this quantity. And according to the condition 6, we got that this is less than or equal to 0, and the delta derivative of v is less than or equal to 0, so the function is a non-increasing function on this time scale interval. Now norm of ep t comma t naught xt is equal to this. We can add and subtract x naught, and we can play with this one, and we got that this inequality. Now taking the help of the non-increasingness of the function v, we can have this vt is less than or equal to em times norm of x naught, and again we can take norm of x naught common, and we can do some simple computation, and we got that norm of ep t comma t naught xt is less than or equal to m plus 2 times norm of x naught. Now if we take m plus 2 as beta, then we got that norm of xt is less than or equal to beta times e circle minus p t comma t naught norm of x naught, and this is according to the definition of exponential stability. We can say that the dynamic equation 1 is exponential stable.
Oh, sorry, can I comment? The second equal should be less than or equal.
Yeah, this one?
No, the second equal on that page. Triangle.
Yeah, here. Less than or equal to.
Is that from the paper? Can you still fix that, or?
No, it is not from. In the paper we have less than or equal to.
In the paper we have less than.
Less than
Okay,
or equal
good.
to. Here it is a mistake.
Okay.
Then again we have this theorem, that is we assume that integral t naught to t of this quantity is tends to minus infinity as t tends to infinity, where t is again the same which we have defined in 7. Then the dynamic equation is unstable. Here is the proof. Suppose that the dynamic equation is stable, then what will happen? For every epsilon positive, according to the definition, for every epsilon positive, each solution of equation 1 satisfy this condition, and we define v, the Lyapunov function, as in A, and from the again the computation of theorem 13, we got that delta derivative of v is less than or equal to norm x of into this integral. Now again we use the fundamental theorem of calculus, and we use this inequality here, and we got that Vt is less than or equal to epsilon times this integral. Okay. Now this integral we have assumed it tends to minus infinity. So Vt again tends to minus infinity, and we got that v becomes arbitrarily small, which is contradiction because v is positive definite, and hence our assumption that the equation is stable is not correct, and we must have the equation is unstable. Here is the corollary based on this theorem, that is we assume that integral sigma t to infinity of this is equal to dt plus t raised to alpha for some alpha positive, and t belongs to this time scale interval. Again the same d which we defined in 7, then the dynamic equation 1 is unstable. Now we give here a couple of examples to illustrate our results. Here t naught is greater than or equal to 0, and we assume that alpha is not equal to -1, and we consider this linear dynamic equation with pt equal to alpha and pt equal to -1 or 2. If we take time scale to be real, then this equation reduces to ordinary differential equation, whose unique solution is given by xt equal to x naught e to the power -1 or 2 alpha times t, and the exponential function e circle minus p tau comma t comes out to be this one, and dt, that our term dt comes out to be 1/2. Then also we observe that the integral sigma t to infinity of this term comes out to be 1 or 2, which is equal to dt, and hence the condition 6 satisfied for all t greater than or equal to t naught, and then hence according to theorem 13 we can say that the dynamic equation, the differential equation is stable. Now let us take t equal to n naught, that is discrete case. Then the dynamic equation reduces to this one, and whose unique solution is again given by xn equal to x naught 1 over 2 times 1 plus alpha to the power n minus n naught, and the exponential function is in this way 1 plus alpha to the power t minus tau, and again dt now is dn, which comes out to be 1 over 2 times 1 plus alpha. Again here we notice that the integral sigma n to infinity of this term comes out to be the summation, and it is 1 over 2 times 1 plus alpha, which is dn, and again the condition 6 holds, and according to theorem 12 we can say that the dynamic equation, which is now here it is difference equation, it is stable. And here is the graphical representation of case 2, that is discrete case with alpha equal to 3 upon 2 and alpha equal to minus 3 upon 2 over here, and 3 upon 2 is this side. The next example, again we take t naught to be greater than or equal to 0, and we consider this dynamic equation. On the right hand side we take 0. Then pt, we observe that pt equal to alpha, and we notice that since pt b is 0, so dt is 0, and automatically all the conditions of theorem 16 are satisfied, and hence again we take t equal to r. Then this dynamic equation reduces to this differential equation, whose unique solution is this way, and which is exponential stable according to definition 11, and also the condition 6 holds because dt equal to 0. For the discrete case, if we take time scale to be square root of n naught and t naught equal to n naught for some n naught fixed natural number, in this case the exponential function e circle minus p square root of n comma square root of n naught, this comes out to be this one, 1 over this for all n greater than or equal to n naught. Now suppose phi is delta differentiable function which such that for given epsilon positive and for fixed n naught we have this inequality. Then according to the theorem 3.7 second from the reference Anderson, Oinsuka, the paper title is Haier-Ulam stability of first order non-linear homogeneous linear dynamic equation on time scale. So we can guarantee that there exists a unique solution x square root of n such that which is of this form 22, and of this equation, of this dynamic equation, such that this mod of this quantity is less than or equal to epsilon for all n belongs to n naught, that is all whole number. So clearly we can say that the x satisfy this one, and according to definition 11 again we say that the dynamic equation is exponentially stable. Here is the graphical representation of the solution of case 1, that is continuous case of this the example, that is alpha equal to 2, and it is on the left hand side, that is blue colored, and for alpha equal to minus 1 it is on this side, green color. That's all. This is the conclusion. So we have derived several sufficient conditions for stability, asymptotic stability and exponential stability, as well as instability of linear dynamic equation time scale. Of course, we emphasize here that the further study on the other stabilities, controllability and observability can be done along with its perturbation counterpart. That's all.
Questions?
I have a question. I guess I saw that you require both circle minus p to be continuous. What is the reason for that? Because somehow it must be partly continuous.
I think you can see the position. You know what it means.
Or minus p in the very first pages, I guess.
Yeah.
Yeah.
Yeah, that's. How does it come into play?
Here in the proof,
Yeah, in the proof,
we need this to be continuous.
but I think you can draw the position. A couple of slides, you will see where we need it. A little bit more. After the capital D defined. No, after the capital D definition.
Plus stability definition.
The D, the big D. Or one page.
Oh, there are 2 pages back now. Oh, yeah.
Yeah, see that limit here. So that's where we need it.
For this dt.
Somehow there should be a way to just omit it. I don't know. For instance, in example 2, you had a general example, right? Example 2. You had a constant coefficient. P was constant, but in this case, O minus P is not continuous. Right?
Yeah, this is
Yeah.
example, we have taken it as constant.
Yeah, here P is constant, but O minus P is not continuous here. Because if you have arbitrary gradients, because you have mu in the denominator, right? It will be continuous.
Yeah, for these time scales, this example is not true. But I think he not only did it for R and root of n or something.
So
It eliminates sometimes, you know.
yeah, it should be eliminated somehow.
So it will be minus alpha over 1 plus mu alpha.
Right. If you have mu there, the problem is only continuous, right?
Yes, yes.
So if you suppose that mu is continuous for the time scale, okay, no problem.
Then you need to determine the times.
Yeah, so we need, is that example also like that written in the paper?
Yeah, this paper, this example.
Because for that can only be those time scales where mu of t is, otherwise you need to change your alpha.
Alpha, yes, yes.
Yeah, we don't need it constant. We need it so that the circle minus p
Yes.
of is constant, is continuous. Yeah.
Otherwise, we have to mention here about mu or particular time scale.
I also have a question on this slide. Why require T naught to be greater than or equal to 0, and not just an element of the time scale? Like, what's wrong with T naught is negative 2, if that's in the time scale?
That is just we have to consider only the positive part.
Okay.
So nothing is not any specific reason.
Okay, it's just the case you put yourself in.
I have a question about theorem 12. It was the main theorem on the stability.
Yeah.
And the theorem,
Theorem 12.
You just passed
yes, could you explain what is x of t in this theorem? I mean, in the statement of the theorem, what is x of t?
This one? It is the solution.
So the assumption is that this derivative is negative semi-negative for every solution of the equation, or do I understand it well?
Yes.
No, you cannot assume that. Again, I don't remember how this is written exactly. It should be like that. You cannot assume something about every solution.
That was my point. Okay, and this delta derivative, this means you compose the function and then differentiate the total function as a function of one variable. Is it correct?
Yes.
Okay.
It becomes one
Okay.
variable.
So, and I have a question about theorem 14 also. then in the proof, you said by contradiction that the limit is not zero and it's something. What if the limit does not exist? So is a part of the theorem that this limit always exists?
This one?
Yeah, the condition 15, what it is?
Yes.
Yeah. So if this condition is excluded, then the limit must be zero, you said. I'm asking, could it happen that this limit does not exist? That's my question. If this limit does not exist, because then the proof would not be complete. Or is it part of the statement of the theorem that this limit always exists?
That's not the negation of
So maybe think about it. Maybe I just don't understand properly of your proof, but this was my question. Thank you.
Okay, let's thank Sanket. We can start 50 minutes earlier. Let's do it now. We want to go to the campaign party. Once you have a problem, definition of your problem, particle to the speed, you don't need to associate it. So the last talk today is about two-order discrete function equations. So Aldo Pereira is talking about that.
And I know they usually meet every year in Brazil. I don't know what you're doing all the time in Brazil. Yeah, but last time we met in Poland last year. Yeah, and then of course during the Corona time, I know it was very active participant on our EBC meetings. Yeah.
Okay, hello everyone. First of all, thank Jacqueline, Tom, and Sabrina for. Better? Hello everyone again. First of all, I would like to thank Jacqueline, Sabrina, and Tom for considering me to participate here. Happy birthday, Martin. Many wishes for you. My talk here involves some works and papers already published on ongoing works involving starting point quite simple. Probably most of people already know here this formulation. Let E, capital A, be a closed linear operator defined on a Banner space X, considering several or some formulations of the abstract Cauchy problem, here showing the first and second order case, where the function f is a function with values in that space X. Here, the central focus is not also the solution itself, but the families involved and the expression of those solutions. That is, for the first order case, we consider the semi-group capital T, and for the second order, consider at the beginning the cosine family, then associated to a sine family also. The interesting thing is, well known by the theory in the real case that this semigroup and cosine functions satisfy these inequalities perspective. So, in order to get a unified formulation, we can set, by integration, every one of these formulations to get a very similar formulation relating them. In this case, the family generated, but this integral version of these equations is called regularized, or strictly talking AK regularized, becoming the participation of these characters here. This formulation canonify C0 semigroups, cosine and sine families, convolute semigroups, and among others. Okay, there's a little example for C0 semigroups. A and K is identically equal 1. For cosine family, we have these inequalities, and then the related ones for the case of sine family. Also, around 2012 or 2013, in addition, from this integral formulation, a general resolvent family satisfies this inequality along with this functional equation. This independent of the equation or the abstract problem involved here, you can set by double integral, many technical lemmas and intermediate results. We eventually ended here. So this kind of unifying, this is true for C0 semigroups, convolute semigroups, cosine and sine families, fractional resolvent families, among others. Simply, this operator is the final convolution here. So, what is the value of involving time scale here? What is for me, at the beginning, there were no reasons for considering only here in this, for this equality holds for the set of real numbers, but trying to involve several works appearing in the last years involving, for instance, C0 semigroups or cosine families, using strictly these equations, okay, this equation here, it tries to set for which cases we can define these families by this and not actually by the problem itself. My main motivations to study here is several works and books appearing in the state. The first one is a book published in 2014 involving discrete semigroup cosine and sine families. Then I remember Jacqueline talking about C0 semigroups of type K, what was actually my first approach for this theory. Then a couple of years later, I working with Jacqueline and my colleague from Talca in Chile, Rodrigo Ponce, giving a word about the second order dynamic equation, again results about expression for cosine and sine families. After, by myself and Rogelio Grau from Colombia, we were able to get expression for fractional resolved families where the ratio of the derivative becomes between 0 and 1. The main idea or the main purpose here is present the possibility, or at least a conjecture, to obtain a discrete counterpart for my functional equation, try to involve as many families as possible at as many time scales as possible. So, in the beginning, a few preliminaries about time scales. For the sake of this talk, I will consider forward jump and backward jump, formulations involving possible delta derivative and then nabla derivative. If possible, in considering derivatives, also consider delta and nabla integral. Okay. Also, I will consider the notions of regulated functions, RD continuous functions, and functions. Okay. For the second notation, we denote by this symbol CRD, the class of RD continuous functions, tend to be TB at a scale containing the point B is such that satisfies this condition here. And finally, but not for all the sake of the talk, I need a definition of generalized exponential and then Laplace transform. So for a function regressive function, the generalized exponential is given by this expression and recovering the the usual exponential function when the scale is for the case of real numbers, and then we can define the Laplace transform for a regulated function and a parameter lambda, such that lambda is regressive and such that the improper integral here is convergent. Okay. There are too many formulations involving delta and nabla derivatives. In the beginning, I would consider only delta derivative, only nabla derivative, or why not consider mixed derivatives, one delta, one nabla, or vice versa. As a consequence, an important task is to choose an appropriate formulation of the problem. We had, in my opinion, there exist too many possibilities to progress for considering here. Also, the main idea is self-population must not extend my equation for the case of real. The equation one was the integral original formulation. From now on, we can settle in formulations involving only delta derivative, not considering now mixed derivatives, and in this case, no delta and nabla, and at least here, not nablas, but only delta derivatives. Okay. We can, for the sake of remembering, the constant semigroup arises from the solution of this dynamic equation. For cosines and families, from this another dynamic equation, depending on the cosine or sine, depending on the initial conditions considered for this equation, and also fractional resolvent comes from this expression, where also we want to set the specific expression of the fractional derivative. Okay. Now, it's natural to think that formulations are not the only admissible ones, but each of these has its proper initial conditions. Okay, the main idea is the same as the case of real numbers, that is considered some kind of delta integral of E, which leads to consider all the previous ones into this formulation here. In this case, the kernel A is a RD continuous function with this domain, and the kernel K is also a function whose values belong to the space X. Okay. For this equation, we can consider also the notions of classical solution, which is as a function RD continuous that satisfies the equation 3 in a distinct order, or my solution was considering the U is not necessarily differentiable, or at least for this case, delta differential. Now, this is so nice, but the main idea is try to get my conjecture starting from this equation from now on. Okay, what is the main problem? The constraints we have to consider from now on. One thing is my equation itself to consider, and now where this formulation can be valid from now on. The main problem is the following one. For semigroups, we have this functional equation. What is the main problem here? That this equation does not hold every time scale, for it's not necessarily true that given two numbers in a certain time scale, that scale itself is closed considering sum of elements. For instance, we need to impose an additional conditions on the scale itself, that is the following ones. First, consider the point 0 belonging to the scale, and then giving 2 points, we force that the difference of this point is still belonging to the scale. There exist several consequences, so strong consequences. What is the following? Is the difference belong to the scale, also the sum of such numbers belong to the scale. The more restricted is the one. Every point is in my scale from now on, all of them are rightness, or all of them are right scale. This discards the possibility to consider this case defined as union or closed intervals. But these type of scales are not closed under summation, so this behavior, this forced behavior, discards all of these possibilities. And in addition, if mu0 equals to 0, the only scale satisfies this condition is the set of non-negative real numbers. So we have not too many possibilities. But still, having chosen a formulation of the problem, the main idea is acquire properties which allow to set a conjecture and try to obtain that this conjecture can be true or not. The starting point, only to define resolvent operators in a proper way, we can consider a formulation involving Laplace transform. Given a RD continuous function and a parameter omega such that the integral involving the Laplace transform is convergent, let lambda such that satisfy some quite technical conditions. In this case, or under these conditions, U is a minor solution of 3 if and only if the Laplace transform applied to this parameter lambda belongs to the domain of this equation, and then its Laplace transform itself satisfies this inequality involving the kernels K and A. The idea of the proof, I will not give the details, but the main idea is simply considering the definition of my solution, and over this formulation, apply Laplace transform, okay, be obtaining this not so nice equality, but after some work, we can recover this expression here. This is necessary to define my general resolver family depending on the equation from which come my integral version. The definition here is a strongly RD continuous operation R, capital R as a generic one, is a resolver family generated by A if there exists some omega such that this condition is true, and the explicit expression of my Laplace transform involves again the kernels A and K. It satisfies this equality here. The good news is the following. C0 semigroup, cosine family, and sine family is still, at least for the case we have considered here, satisfies the same expression of Laplace transform as in the real case. So these expressions are true independent of considering real numbers or natural numbers or even multiples of a certain parameter positive h. For the three cases, the expression of Laplace transform in a beginning, writing like this, are the same as the original ones we know from course of differential equations. Also, we have some generic properties involving all resolver families defined by this approach, again, involved from the idea of Laplace transform to defining my operators. Still, we have this equality, very similar to the real case. This belonging or commuting with the generator A, and this technical equality to be true. Also, for the sake of time, the domain of A involving as a comment, it depends on the specific expression for the question involved here. For the case of semigroups, the domain of A has different expression depending on the behavior of the point zero. If the point zero is right dense, the definition of the domain of A is the same as the case of the real numbers, but also there exists a discrete definition of this domain where zero is right scalar. For the second order, there exist three possibilities of the domain of A. I will not give the details here when the idea is try to set my conjecture here. But for the case of semigroups, it is still trying to set my first step toward my conjecture. Here we recover the idea for this discrete equation here. Again, recovering the idea of the Laplace transform, but was And then by the uniqueness of Laplace transform, my solution is given by the semigroup operating over the element x, whose expression is given by this kind of exponent, the discrete exponential. Also, not only the integral formulation given here for the case of discrete scales, also this expression allows to obtain this kind of integral formulation involving the semigroup and some kind of convolutions. The good news is this still becomes to be true for second order discrete equations. Again, the use of Laplace transform allows to obtain these expressions, and by uniqueness obtain cosine and sine family, some explicit expressions, and then we can set a second result which in structure is very similar to the one for the semigroups. Okay, I decided only to show the formulation here for cosine family, but as here, the same arguments allows to obtain a very similar relation for sine family. That is, shifting all capital C's, replacing for capital S's, denoting sine family, and then appear a parameter n here, and here a parameter m. So the idea is get m and n integer multiples of the parameter h in order to equations to be true. Okay, that seems to be nice because first and second order cases are covered. What is the next step? Fractional calculus. Yeah, it can be very complicated, but it's still true or similar expression for fractional order equations. Let's see. The main problem with fractional equations is the fact that you need to still define a fractional kernel. For the real numbers, it involves a fractional power of a parameter t. So the first step before trying any conjecture is define the discrete counterpart of this kernel here. To do this, consider alpha real number and h positive, defining the funny monomial as this expression, depending on the parameter alpha is still a real number, a natural number, integer, or when not, you have these expressions involving gamma function. With this, we can...
Sorry, this is now only good for the continuous and discrete from now on, right? Does it mention discrete?
Yeah, for this definition, I will consider only the discrete counter. This title is as part of the discrete counterpart of the fractional kernel. Only this.
Does it mention a discrete definition?
The H is for H is E, right?
Yeah, the idea is to be true for C H times C, not for real numbers. It's not exactly equal, but...
So only HZ, right?
Only HZ.
Okay, and it mentions the definition in, let's say, Goodrich-Peterson book?
Yeah, I remember the right one is very similar, but I guess that I try to remember the book of Goodrich and Peterson considering only the case H equals 1, I guess.
Yeah. And in that case it matches?
Yeah.
Okay.
This is a little more general in the sense we're considering any H positive and not only H when H equals 1, that's in that book.
Yeah.
That's. With this Foley monomial, we can define this not so nice expression what does it mean? H step alpha order fractional monomial, where alpha is a real number, not considering the -1, -2, -3, and so on, and adopted also the following conventions. When alpha equals to 0, this kernel equals to 1, this part, and in case of I get division on a ball, I define this automatically as 0, in order not to get problems with this object. This object has several nice and maybe not so nice properties. was the following. The more interesting ones are detailed here. When h goes to 0, we can define this kernel with h equals to 0 as the usual fractional kernel from the real numbers, and a shift of the parameter from alpha goes to alpha plus 1. Unfortunately, this kernel admits delta derivative, and also this my kernel does, and also this kernel allows to define a fractional sum or fractional integral by this expression. Well, the most interesting one, at least for me, is seen as an operator. This kernel is not exactly but multiples of n, but it needs to start from this point. It's a kind for derivative and also displacement of the scale, which is quite interesting. But still, this kernel admits Laplace transform, and again, this for general h, it recovers this expression, but it's not exactly the interpolation generated by the Laplace transform of this kernel. This then is the fact that this numerator not equal to 1 appears is at the beginning quite strange, but seems to be right in order to get the same approach in the case of integer order dynamic equations. We can see. Then the idea, maybe the most simple equation, is considering the order of the derivative between 0 and 1, considering the Caputo fractional derivative of order alpha with the starting point A, B, and step h. The recent properties, or given before, allow again use the Laplace transform giving to this expression for the Laplace transform of my solution. Again, the appearance of this kernel in the beginning completed all of this, but again by using this we obtain this the fractional operator, again alpha between 0 and 1, whose expression is the discrete counterpart of the Middle-Level function with this parameter h to alpha times the operator a, and again this following monomial. The good news is this is still my conjecture seems to be right. Again, the integral formulation for the discrete cases becomes this, which is not so nice, but the main idea is noticing that the structure of this equality is the same for the first and second order cases. Also, this allows to obtain a similar relationship where considering the Riemann-Liouville derivative. Again, I compare some similar expressions here, and then, okay, but Riemann-Liouville derivative again for when alpha alpha is between 0 and 1, but we have the same difficulties as the case of real numbers, but is this parameter. But using some properties of gamma function, with alpha again between between 0 and 1, we obtain this inequality, but it's quite similar for the case of real numbers, and still this, the counterpart of the fractional resolving operator still has this property. But still, we can obtain a similar relationship for this kernel. This is quite similar to the last one. I don't know, in order to finish the talk, I would like to say at this point that the conjecture seems to be true. Try to find a right proof for saying definitely this is true. What is this? This equation marked with a star is at the beginning defining the finite convolution for the discrete case. We can therefore conjecture that this equality, which is the discrete counterpart of the first one, is true for all these families. But I would like to set up a proof which inspired by the real case involving double integrals and maybe double Laplace transform, but I'm not sure. But in the last couple of years, I have some doubts about the trueness of this equality because of the following way. In the last years, some authors defining this kernel arising from the Poisson distribution. In order to this is used to define not exactly a discrete semigroup, but a discretized semigroup using this kernel. Also, the main idea can be applied to second order difference equations in defining discretized cosine. This can be true or not because of these inequalities. The discretized semigroup satisfies the same equation, but as the real case, but the discretized cosine does not satisfy the same equation for the real case. But this additional test, in my opinion, adds some kind of noise into the parameters. Nevertheless, this family and this another family satisfies this equation. Again, this appearance of this kernel, again involving this some kind of Poisson kernel defined is true. So I'm going to finish here. The main ideas here is trying to conjecture this classic equality is the same equality presented before by these guys. I still have no idea because this class equality, I'm not sure if this applies for fractional kernels yet. There has no information about fractional order for this process of discretizing. And then try to, if not, try to set some similar equalities to here involving these fractional kernels, and then try to say that this equality is or not true actually, but there's still some work to be here. And why also, or why not, try to set all this work to a Nabla case and try to get again semigroup or cosine or sine involving Nabla, Laplace transform, Nabla exponential, or Nabla regressivity. Trying to get this mirror behavior. I will stop here. Thank you for your attention, your patience, and again, Martin, congratulations for your first 60 years of life. I understand many years of life ahead. I will stop here. Thankful to you.
Questions?
So to include more time scales, you have to, the n plus m story, right?
Yeah.
But we had the same problem, right?
Yeah.
In our periodicity thing, n plus omega. So we did it somehow, so maybe you can also do it somehow.
I still have no idea. I don't consider it yet arbitrarily.
But the strategy is clear. First, you have to do it for a time scale which is in the middle, which is not one of those, just one. And I would suggest the quantum time scale.
Yeah, but the problem of quantum time scale is the fact that the points are not close under summation. And there's some subtraction.
Yeah.
But the beginning, before I define it by conjecture, I decided I need to put this condition of to scale to be close under subtraction.
Yeah, but in order to prove it for all time scales, you need to remove that condition. You have to replace it by something.
Necessary, yes.
Yeah. And the only way to see how that, or I tell you our way how we saw that, first to Q, then to isolate it, then to general.
Yeah, but I still can isolated time scale in order to set the general case. But I guess that moving the closeness and the addition is too restricted for a general formulation.
Yeah.
More without time scale. Maybe it's too much for considered our case.
Other questions? If not, let's take it out of our time. Jacqueline has an announcement, I don't know.
Martin is right.
Okay, just a very quick announcement. As you know, we have tonight Gambay night, so it's possible to go earlier if you want. So we go directly from here. There are like people there waiting for us. The students got a table for us, so we can arrive there and start the Gambay night. So, and today it's included the beer and some appetizers. So I hope, and soft drinks. Yeah, I hope everybody enjoyed the night. So thank you very much.